And then we're going into the morning session. We're having two different ones. One on data and what you can do with data, what's the value of data, how can you actually employ it in the best way. I've got three presentations that Ricardo is going to introduce in a second. And then we're having, just like yesterday afternoon, an open space session, only this time on what are really the research gaps for the next 3 or 4 years, and maybe even extending for the next 7 years of the task, which we then wrap up in the last session of the day. And in between, we're getting an inspirational session with a few talks from, especially inspired by David Lenaghan, on the journey from deterministic to probabilistic, and what are the pitfalls, what are the holdups, why hasn't everyone switched over yet? So with that, I hand the screen over to Ricardo.
Okay, so good morning. I will be quick because we have 3 presentations and we want to have some time in the end for the discussion. So the plan is to have around 20 minutes of discussion. So this session is about collaborative analytics. So we'll talk about federated learning, data markets, and also the use of cloud computing to forecast time series. So we will start with a presentation from Brad from IBM Ireland about the use of cloud computing, the relation also with some projects they have on energy domain. Then I'll talk about data markets, and Paul will talk about prediction markets. Actually, something to discuss is the difference between data markets and prediction markets. They are different. And something we'll try to explain in the presentations exactly this new concept. So this is emerging as an area of research in renewable energy forecasting, and something for the discussion is also the relevance of these to industry and opportunities that we can take from this research center. So we'll start with Brad. So we'll make this presentation of AI and cloud computing developments towards the integration of renewables. So.
Thanks very much. Good morning, everybody, and it's nice to be with you. Thanks for the invitation to join you this morning and to be here today. So in this talk, in the few minutes that I have with you, I'd like to talk about 2 different technologies. One AI technology, machine learning technology, and that's the technology of graph neural networks. I'd like to talk a little bit about a cloud computing technology called serverless computing. And in both cases, I want to share some of our recent work and experience and results in applying these technologies in the energy domain to make energy forecasts at different levels of the system. And I want to kind of tie those together with how they can be used indeed as part of a market. In this case, not for predictions and not directly for data, but rather for energy flexibility or demand response. So I'll try to cover all that in about 20-25 minutes. So I'll try to cover that in about 20-25 minutes, and be happy to have any questions, etc. at the end. And hopefully some of the things that we'll talk about will help inform the discussion we can have at the end of the session. So from a graph neural networks point of view, what is a graph neural network? Well, a graph neural network is a deep learning method that's specifically designed to carry out inferences on graph data. And in particular, it's a way of applying neural networks directly to graphs. And this is handy because a lot of the graphs are, of course, a very powerful data representation. You can represent a lot of different types of data with graphs. I mean, you can represent images with graphs. You can represent text with graphs. From the energy point of view, of course, the energy systems that we spend a lot of time looking at are also graphs. And one of the reasons that we found graph neural networks to be powerful is because they provide a way to encode your domain knowledge, something that you understand about the system that you're trying to model, into the deep learning system. And this domain knowledge often takes the form of some kind of structure. So in an energy grid, you often know the structure of the grid, and so this provides a way to use that information in a data-driven model. And then, of course, one of the benefits of encoding your own information about the structure of the system in the model is that you end up with deep learning models that have fewer parameters, which are therefore easier to train, require less resource to train, less prone to overfitting, and these kind of problems. And so to get directly to an example, here is an example of a graph that we've used to model part of an electricity distribution system. And so if you look at the picture here, maybe it's a bit upside down from a typical view, but what we show here is at the top nodes in yellow, there at those nodes, we modeled the voltage at end users of the system. In this project, we called those end users prosumers, right? To account for the fact that actually, if you put solar panels there, they might be producers or consumers. So the term was prosumer. And then the layer of green nodes below that is actually what we model as the energy on the feeder that is serving those prosumers. Those feeders, of course, come from substations, and then we take as known the energy load across the portfolio of substations. And so, of course, in principle, if you know the structure of the system and you have all the physical information about how all these things are connected, you can run a grid simulation and get exactly the information you're looking for at the end nodes. If you know the demand, if you know the size of the conductors and everything, you can run a grid simulation model. In practice, and particularly for distribution systems, this information is often not exactly available, right? You don't know the exact demands. You have a sense of the physical layout, but you might not be exactly right. And in terms of being able to get there with grid simulation, maybe you don't get where you want to go. And so the approach proposed here, the use of graph neural networks, is a data-driven approach, and it's kind of a middle ground. So you see that we use a graph to encode what we understand about the structure of the system, and then we use data to kind of fill in the gaps and to provide some predictions. So from a modeling point of view, what we do is that at every node in the grid, or every node on the graph, we have the variables that we observe, whether that is the voltage at the prosumer, or whether it's the load on the feeder, whether it's voltage across several phases. Right, we have the variables that we observe, and then we also at the nodes take features which we compute from those variables, in particular lags, right? So you might lag by 15 minutes, 12 hours, 24 hours, et cetera, because this is a highly correlated variable. And then we also include, in this case, exogenous variables, in particular weather data. So temperature, could be wind speed if that was relevant for the case, solar radiation, and also lags of those things. So you end up at every node with a matrix of variables, right? Which then we encode to a lower dimensional state space using a neural network. And that encoded state kind of is the representation of the system at that node. And then in terms of the graph, on the edges, what we implement is message passing, again, with a neural network. And what that message passing network does is translates information, it propagates information between the nodes. And so what we've done with the GNN is to say, I know that the nodes are connected, right? So I make the connection, but I don't really specify how they're connected, right? So you don't put a physical equation for the connection, rather you put a network and you let, through training, you let the deep network kind of learn how these nodes move together. And so that's the basic idea. And this was deployed at a demonstration site in Cyprus and a couple of other places, which I'll get to in a few minutes. And in the Cyprus deployment, which corresponds to the graph I showed you on the previous slide, we had 28 prosumers fed by about 25 feeders coming through 15 substations. And the picture at the bottom is just a picture of the data ingestion for that case. The red line is a cumulative number of points. There were points coming in at different time scales from every minute, every 5 minutes, et cetera. For the purposes of this work, we averaged everything to 15 minutes. So to just briefly share some results, I wanted to share here one of the comparisons between the predicted voltage and the observed voltage at one of the prosumer sites. And this is over a period of about 4 days. And what we are, again, looking at here is what's the voltage at the end of the grid. And the reason that we're looking at voltage in particular is because we wanted to understand the behavior with respect to like potential congestions on the grid. And this situation arises as there are more distributed renewable energy resources at the edge, right? These are things like solar panels on the roofs and batteries in houses and the needed commercial premises. The idea here was to eventually to give a distribution system operator some insight into how things might be moving and happening at the edge. And we see on balance, right, there's pretty good performance, pretty good correlation between the observed values and the predictions. And then you also see kind of, we talked about probabilistic in the introduction, we see some error bounds for the predictions. So that is the one comparison, between actuals and predictions from a GNN point of view. And one of the other things that's interesting to look at and to think about is how does this GNN approach compare to, for example, other data-driven approaches, other AI type models. And so to provide some kind of comparison on that, we also trained a couple of kind of regular neural networks, just multi-layer perceptron networks, and autoencoders, each with 2 and 3 layers, as we see here on the graph. And the idea was to provide some kind of comparison between the GNN approach that we developed here and the kind of more traditional AI approaches. And what we see is that the performance of all the models is comparable in terms of the mean absolute percentage error or the root mean square error. The performance is fairly comparable across all the models, but if you look at the number of parameters, the GNNs have considerably fewer parameters than the other approaches. So there's a quick 2 or 3 graph neural networks, but that is what I wanted to share about the work that we have done there. And I want to move on now to talk a little bit about the technology of serverless computing. And serverless computing is a very interesting technology, particularly for time series forecasting, particularly for forecasting cases where, unlike the big model that we had for a graph neural network, you might have rather lots of small models, right? You might have models for every house or every premises or every substation, but you have then a lot of these models, and serverless computing is an interesting technology to manage these kinds of models and to run them. And in contrast to the name, serverless computing doesn't mean that there's no server. It just means that as the person running the workload, you don't have to worry about the server. You use a cloud computing provider to manage the servers behind, right? So that the forecasting jobs or the serverless functions jobs just run quite quickly, and then the resource behind those goes away. So in terms of cloud providers, right, there are many cloud providers, and they all offer some variety of serverless computing. From IBM's point of view, our offering is Cloud Function and Code Engine. From Red Hat's point of view, there's a implementation called Knative. At Amazon, it's Lambda. At Microsoft Azure, it's Functions, right? So all the cloud providers have this serverless technology. And what I'm showing here on the graph is a comparison between the cost actually of running workloads on serverless versus a full-time server, in this case, a Kubernetes server. And what you see is that when the job duration is low, and the time on that's the horizontal axis, and the vertical axis, the time between jobs is also high. So you think about like running a forecast every few hours, and that forecast, when you run it, actually only takes maybe a few minutes or seconds to run. The average utilization of that workload is quite low. But if you want to run lots of them at the same time, the peak is high. And so serverless provides a way of doing that and managing that workload with very good horizontal scalability. And we'll look in a few slides about some of the results we saw about this scalability. Okay, so what we did with serverless was to build a forecasting system based on this technology. And the idea here was to provide a system to make what we call value-added forecasts, where you combine the historical information from the time series that you're interested in, also with exogenous variables of business data, weather data, etc. And the idea here was to train a small model. In this case, we used a generalized additive model, relatively small. It's not a deep learning model, but we wanted to train a lot of them. And we wanted to use some semantic information to actually automate the training and deployment of these models. And so in this case, we provided a semantic layer, which we stored in a graph database. The semantics that we provided were around entity and signal. So entity is basically just where the observations take place, and the signal describes kind of the what. And with a bit of type information, what this allows you to do is to say, okay, I have a type, the substation energy load, for example, and I want to use the same model structure across all of them, but I want, for every substation, I want the actual parameters of the model to be different, right? And so this provides a way of doing that. So here's a view of the deployment of this system, and I know it's a bit small, but what I want to draw your attention to are the substations and feeders here at the bottom, because this is the same case in Cypress that I showed for the GNN case. And really the idea is to, again, use the semantics to automate the deployment of the models across the system. So in terms of results for serverless, using serverless to make forecasts, we had a system that was not massive, right? But that showed some interesting performance with respect to horizontal scalability. So on the system side, that's the table on the left. We had forecast models that we were using generalized additive models, like I said, together with weather information and lags and some calendar information. And those were running in containers that had a couple of CPUs and a couple of gigs of RAM. That was the workload we were looking to scale horizontally. So the table on the right corresponds to scaling that horizontally. Now the time series database and the graph database, which were not heavily resourced that you see here on the table, there was just one instance of those, right? So when we parallelized the forecasts, we just kept the same time series on the graph database. And this was perfectly adequate for the case that we were working on. And it showed some interesting scalability as we moved more and more jobs in parallel. So what you see is that as we added more jobs in parallel, there was a bit of leveling off in terms of the total throughput. That was actually not to do with the limitations of serverless, but rather to do with, hammering the single database instances that we had. Okay, so that's a quick tour through serverless computing and how it can be used to make time series forecasts and to manage lots of time series forecast models. And we talked a little bit about graph neural networks. So I want to give you some sense of how this can come together in a wider system. And in the case that I talked about here, this came together through an energy trading or an energy flexibility trading or demand response trading system developed as part of the GoFlex project, which was a Horizon 2020 project. And basically the GNN piece and the forecasting piece that I talked you through formed the right-hand side of the diagram that you see here on the left. So this was provided so that a distribution system operator could actually make bids for demand response or energy flexibility from a market where the sell offers into that market came from prosumers on the grid, be they industrial facilities or consumers. And the idea, like I said, was for the distribution system operator to be able to bid for some of this flexibility. And the table on the right provides just a summary of some of the results that we saw as we deployed the system in Cyprus and Switzerland and Germany. There were overall about 500 prosumers that were active and thousands of flex offers generated and activated. So that's a quick tour through some of the work that we've done on energy forecasting and cloud computing with AI. More recent work and current directions have followed these same topics, but have been more focused on some of the underlying technology rather than the application. We've continued to look at forecasting models and how forecasts evolve over time, especially when you're making forecasts with a long horizon. And we've also been monitoring these models for things like distribution shift and these types of things. And we've been working in different applications, energy, but as well as supply chain and IoT applications. We've also continued to look at using semantic information, like coming through knowledge graphs, for example, to automate the training and deployment of AI models across thousands of physical assets. So to wrap up, I would like to first off acknowledge that the work that I've shared here today is not just my work, right? It's the work of a larger team. And in particular, I should acknowledge Francesco Fusco's contributions on the graph neural networks, Rob Vormley and Mark Purcell's work designing the serverless forecasting system, and Saishu Tirupathy for doing some of the modeling with me together on the time series forecasts. The work took place as part of the GoFlex project, and for that, certainly need to acknowledge the contributions of Torben Bach Pedersen at Aalborg University. The flex offer concept and mechanism for trading comes from him and his group there. And the deployments in Cyprus were made possible by Ioannis Papageorgiou at the Electricity Authority of Cyprus. So finally, I would just like to say that at IBM Research in Dublin, we're celebrating our 10th anniversary in Ireland last year already, so we're 11 years here now, and we're very open to collaboration. So we collaborate on European research projects, Irish research projects. We also have an intern program that's quite active, and applications for 2023 are now open. So please encourage your best students to apply. Thank you very much.
So we have time, 10 minutes, for the questions. Right.
Yeah, so that's a good question. So I didn't talk at all about that on the slides, but that was quite an extensive part of what we implemented. So the way that we carried this out was that we had a data ingestion, and I showed you one graph of kind of the data ingestion. And then we would have a separate job that ran in the background that would average the data. In this case, we were working in a 15-minute horizon. So we would process the data so that we had basically full information for 15-minute horizon, or for 15-minute steps in most cases. And then in the cases where we didn't, we actually would have a forecasting model that would aim to fill in those gaps so that we ended up with a full 15-minute, full data on that 15-minute step. And then we use that going forward. That's a good question. It took a considerable amount of work to get that piece working right so that the following forecasts can work. Yes.
Just go back to CNN. Is there a danger that for your abstract, towards black box scenario away from the data driven, and that when the errors occur and that you cannot trace it back, it's more difficult to assimilate the data that actually caused the problem?
Absolutely, right? For sure, that's definitely a risk. Anytime you're using, especially a deep learning model, you lose a bit of track as to exactly why you're getting the prediction that you're getting. And that is a gap, right? And I think it's an interesting thing to look at from a research point of view. The trade-off is that with the GNN type model, you can also get forecasts that you might not have been able to get before. And so from a operational benefit, sometimes it's useful to have a forecast that was sort of systematically made, even if it mightn't be the best one. And so it's sort of a risk-reward trade-off to make there.
Thank you for your presentation, very interesting. And in the first application, I used the deep learning model, the physical structure of the network. It is related to the model, or you can also detect the relationship between the variables. One was, that the carbon depends on the demand, was the flow of current. How much learning from the historical data and how much is dependent on the physical structure?
So that's a good question. So what we gave as input to the network was the physical connectivity. Okay, so we said, okay, this prosumer is fed by this feeder from this substation. But the network, through the message passing layer, has an opportunity to exchange information across the system. And to actually learn connections and influences, if you want, that actually weren't coded. And the way that we control that is with the number of message passing iterations. Go back to the table here. In the MP column, right, number of message passing iterations, we tested, or here we reported 5 and 8 message passing iterations. And so these message passing iterations are the deep network's opportunity to kind of learn the connections between nodes that weren't like encoded in the input.
So it's benefiting system too many renewables and also demand variations. So there's so many variations. So it helps that to be detected from the data, just model.
Exactly, right. So you encode what you know about the system in terms of the connectivity, right? But then you provide an opportunity for the system to learn what you don't know. Yeah.
I have a question that might be for you as much as for the room.
Okay.
I know that the TSOs and also producers of renewable power are pretty tight about where their data goes, and are they actually allowing their third-party forecasting providers to run on the cloud, or do they require still to have that on a server under their control?
So that's a very client-specific question, right? Some clients would have different views on that. What I would say from the IBM point of view is that all of the cloud technology that we provide, we offer in a hybrid fashion, which is to say you can use the cloud computing technology, but you can actually deploy it to servers that are under the control of the company. And so it's perfectly possible to run this stuff on the servers that are under the control of the company and take advantage of all the cloud technology, but still retain the data sovereignty.
Okay, so we'll have the discussion also in the end. So some of the questions we can take at them later.
So while I'm finding Ricardo's presentation, Paul, could you send me your presentation, because it's much easier if we run from this one.
You have it on the email. I think you sent yesterday.
Oh, you sent it last night. Okay, then I'll just have to find it. No worries.
Okay. Okay, so I will present what we are doing in Smart for Health project. So Smart for Health project is an European project. I don't know if yesterday George presented the project or not, but no. So it's a European project where we have been addressing different problems. One of them, it's collaborative analytics, collaborative forecasting. So I'll talk about federated learning and data markets. So there is an increasing volume of data that is available, and it's quite valuable for the power system operation, for traders and so on. So Red already touched this point. So there is a lot of data, and there is means to process all this data and store it and have this semantic representation, but there is three main barriers. One is data is either private or confidential. So access to data it's a big problem. Data is valuable. If you cross data and you combine data, you even extract more value, but then we have this problem. But then they can share data if you have incentives. So these economic or non-economic incentives can at least having some of the data owners to share their data, and some industries already doing this in the cell phone, smartphone industry, where we use our apps like Google Maps. Somehow we are giving our data in exchange of a free service of Google Maps, for example. But there is also a lack of business cases for this collaborative analytics in the energy and in the renewable energy sector. What we have been doing in Smart for Health is addressing this problem where we want to combine different power observations, weather data, and also numerical weather predictions, and even different types of data. I have here the example of satellite images and sky cameras, but can be other type of data. So on one side, when you have these observations or this time series, we are talking about privacy and monetization, because somehow your data, you own the data, you don't want to share. And if you are sharing, you expect some kind of financial compensation for that. On the right-hand side, on this kind of data, satellite images and sky cameras is more a question of monetization. So what is the benefit of this data, the additional benefit, and if you are willing to pay for this additional data. So that's the key challenge. What we are doing in Smart for Health, one side is federated learning. This is what I will present in the next slides, and also data markets, algorithmic solutions for data markets. In the data market, our idea in Smart for Health is that the data price is a function of a specific use case. So if you use your data in a specific use case, you can have a price or a value for your data. This is very different from energy markets, because in energy markets, we cannot replicate energy, unfortunately, or natural gas will be very useful. But we can replicate easily data. And data, the value of data is when you combine data with other data. So there is also combinatorial nature on that. And in the case of federated learning, privacy is the key issue, and this is what we are trying to achieve. So with federated learning, we develop a privacy protocol and an approach that can cover these two scenarios. So you have a centralized cloud, for example, that centralizes not the data, but centralizes the communication between the agents and the data owners. They don't exchange data, they exchange other type of information. Or you can have a complete or a full peer-to-peer exchange of information between owners. What is federated learning? So traditionally, we have this approach. So one single data set, even if you have three different data owners, they have their three different colors, you would combine all the data from the three different owners, fit a model, and extract some knowledge from that data. The problem is that if these data owners are not willing to be combined with others, it's available already in the literature called federated learning. You are breaking data into these silos, and then we apply a model to each one of these silos, so with the data completely separated, and then we combine these in the top in the single model. So in the literature and the approach that has been done in the last 5 years, this works very well in the case of what is called horizontal federated learning. So in horizontal federated learning, the 3 different data owners have the same variables, they just have different instances of those variables. So this is what in the smartphone industry and all the developers of apps they have. So all of the data owners use the same app, so same features, but they are different data owners. So we have vertically, or in this case horizontally, different instances or different observations from those owners. The focus of this presentation and Smart for Heads is a problem when you have different variables. So if you have 3 wind power plants, you have the observations of wind power plant 1, 2, and 3. So they are completely 3 different variables. And so the challenge is how to combine this data from the different data owners. What we made in the project, we started with a simple model, a linear model. So we want to forecast multiple renewable power plants, wind farms, PV power plants, by combining the past values of themselves. So the past observations, and build a linear model, like in this case, not an autoregressive model, a vector autoregressive model, because there are multiple variables to forecast with a single model. So we started with this simple approach, and this was already a challenge because when we work on forecasting, the past values that are your explanatory variables are also the target points. So it will be very easy to get the private data from your competitors or your neighbors, so on. So what we made first was an encryption of the data using algebra. So in the end, we get the same model, but all the data is encrypted, including the coefficients we get from fitting this model are encrypted. Coefficients, because if we know the coefficients, this works pretty well in training, but if you know the coefficients in testing, forecasting, you can also get the data from the others. And that was also a problem. So because of that, we make distributed calculation of the coefficients. So each data owner makes their own calculations, and in the end, they get their own coefficients, but they are encrypted ones. And then using the same algebra, we can decrypt or remove the encryption of the coefficients. So in the end, we fit these models distributed, data remains local. Some information is exchanged between the data owners, not the true data or the original data, and we can keep this work and this model fitting completely private. I'm not giving here mathematical details, otherwise it would be a quite boring presentation. What I can tell you is that there is mathematical proofs that guarantee the privacy of this approach. So as I said, we started with this quite simple model, linear model. And then we started to include here the nonlinearities, mainly because nonlinearities between wind speed and power. And we also want to have a very generic model that can be applied in different problems. So for the nonlinearities, first we started with the spline, so an additive model. So basically we have these explanatory variables, and we are making them a sum, an additive sum of key variables using the spline approach. Something that it's relevant is that this is compliant with our privacy preserving protocol. So by doing this, we keep data private. At the same time, we have been exploring kernels because we are not happy with the results with the splines. The problem is that with kernels, in particular the Gaussian kernel, it does not comply with our privacy protocol. So privacy will be at risk. So we made a simplification by removing some parameters of the kernel, and we have the negative distance kernel. So we are working with distances, no longer with observations. So this is the only part with mathematics here. I will not speak about them. Just so mathematically, we show this is compliant with privacy. So with this approach, we have a nonlinear model, a single model capable of forecasting hundreds and thousands of wind farms, PV power plants at the same time with a single model, and all the data is private and all the data is combined. An example for France, there is, I think, 6 or 7 wind farms in France. They are more or less in the same region with 60 wind turbines. This shows the improvement if we use this multivariate model compared to a single model. So this is with ECMWF forecast. And you can see that for 2 days ahead, we have an improvement. In some wind turbines can go up to 15%. On average, something between 5 to 10% of improvement, just by combining data from all these wind farms. There are not so many, but 60 wind turbines is not bad as a proof of concept. This is already known in the literature. It was already published in the past that if you combine data from different data owners, we improve predictability. Even with wind turbines, JETRO published also a paper on that. What it's new here is that we can do this with data fully private, and that is the big advantage. And so with kernels, we are still working on this, but we compare this with gradient boosting. So this is a highly optimized model to making the prediction. So it's our benchmark. And you can see that we outperform it most of the time, at least on average. But the goal is, if you have at least the same performance, is very good, because there is no privacy here on gradient boosting. We are getting all the data, centralizing all the data. While what we are doing, we are completely distributed, and all the data is private, and that's a big advantage. So that was the federated learning. Another concept, it's data market. So here you have the concept. It's simple. So we have sellers of data, buyers of data. One agent can actually be a seller and a buyer at the same time. And in the middle, we have collaborative analytics, can be the model that I presented before. And then, but inside we assess the value, and then we distributed the payments and the benefits between all these agents according to the value of data. Just to show you an high-level description of the data market. So the sellers, they want to monetize their data. They are just interested in selling their data. They know it has some value. They don't know how much to price the data, or where is the value of data. And so they just go to the market to sell their data. That revenue depends how much they are contributing to the forecasting skill of the buyers. So if my data is very relevant to another one, to a buyer, I get more money because I'm giving him more information. So in the middle, as I said, we have this collaborative analytics. It's just a forecasting model. And then the buyers, they want to improve the skills. So they want to buy more data so that they can improve the accuracy, and the payment depends on which seller contributes to their gain they have. So in our level description, this is how the data market works. So Paul will talk about prediction markets. It's a different concept, but very similar to this one. And we develop 2 different algorithms. Actually, in the project, we have actually 5 implementations of data markets. This was the first one. It's called a no regret mechanism. So sellers, they just put that data, and the market operator, they calculate the market price based on the previous market price. So it's an iterative market price. Then the buyers, they put their target data. So they get a prediction from the market operator directly. So they put what they want to forecast, their bid price, and the maximum payment. So how much they are willing maximum to pay. So like a cap in the payment. And the data allocation is made according to the difference between this bid price you have here and the price that was calculated by the market operator. What this means is that you get clean data if your price is similar to the market price. You get data with noise if it is far from the market price, or if it is below in this case. And so all the payments they make, they depends on the game. So the buyers who earn more benefit from get the data from the sellers, they pay more for their data, and they pay according to the difference between the market price and the bid price they made. And then the division of payment by the sellers. So if you contribute more, if seller 2 contribute more to the gain in buyer 1, so we'll get more money from buyer 1. And so this is how the market works. I will show some numerical results about it. One of the limitations is that we don't include here the seller's loss. So if you are selling your data, you have some loss, and it's not included in the model. Another limitation is that as a market, this is somehow strange, because we start by setting a price, and so the price depends on the previous one. So if we look at energy markets, for example, it's not very consistent, let's say. Another implementation that we made is on social welfare maximization, and this is very close to electricity markets. So basically, the sellers, they put their data there, the minimum price they are willing to get for their data, and buyers, they put their data, the target data, and the maximum price they are willing to pay for their data. And basically, we make this maximization between buyers and sellers' loss. And from this maximization results a market price. So this is very, very similar to electricity market. Instead of buyer gain and seller's loss, we have demand and supply. That's the only difference. And then we have to make the forecast back to the buyers, and they pay according to their gains, and then we distribute these by the sellers. So this is how this market works. A big difference to the previous one is that we can include there the seller's loss. The buyer gain is easy because you buy your data, you use your forecast for the market. You know exactly how much you gain. The seller's loss, it's a different story. Okay, it's just a result. We made a toy example for Nord Pool with public, well, it used to be a public data. Recently, Nord Pool is asking 500 euros for access to their data, but it used to be a public data. From the trading areas of Nord Pool market. And we put here these wind rows just to underline. You see that frequently the wind blows from Copenhagen area and Malmö from DK1. So they usually blows from DK1 to DK2 and SE4 in Sweden. And as you will see, this is relevant for the market results because we have here a clear separation. So each one of these zones are like agents in the market. So all these 6 zones, they were selling and buying data in the market. They were buying and sellers at the same time. There were 2 agents, SE4 and DK2. They earn a lot of, this is the additional revenue for using data from the others. And the blue one are the additional revenue from selling their data. So these 2 agents almost earned nothing by selling their data. So their data was not very relevant, but they had big improvement on the revenue in the market by having improved forecasts as a result of the data from others. And the biggest supplier of data to them was DQ1 because he earned a lot of money by selling his data, and the revenue in the market was not a great performance, although we also benefit from it. And if you look at the wind rows, we see clearly there was a strong relation strong correlation of dependency between these agents. So the market was able to realize this. Again, this is a toy example. If we go to real implementation, there is other challenges. Okay, and then we implemented these in the project in the prototype on IOTA with blockchain. IOTA is a distributed ledger technology, a public distributed ledger technology that was created in Europe, and it is nowadays a foundation in Germany. So it's one of the leading distributed ledger technology in Europe, and we implemented all these data markets using this technology. So there is IOTA as a cryptocurrency that you can exchange by any currency, official currency, let's say. And the way we designed everything is like a typical market we have on electricity. There is a market session, a bid placement, market session that is closed. We run a market clearing, and then we clear the market, and then there is this exchange of money and data between the agents. Just to conclude, in Smart Forecast, there is actually a portfolio of data market implementation. So, and it was already published, and it's easy to find. So that first paper was what I was telling about the no regret mechanism, and RPR Panson and DTU, they published 3 different implementations of data market. And actually there is a 5th one, the social welfare maximization, that is not yet published. So we are creating a zoo of data markets, and there is a reason for that. It's not, as in my conclusions, it's not yet established what is the best mechanism and what is the most fair mechanism for data markets, and this is very important work for the future. So these advantages of a federated learning approach, and I think it's important to highlight these, you only have to maintain one model. So you can use one model to forecast all wind farms or PV farms, and you even get a higher performance. So this is an important advantage. The value of spatial temporal information is already a proven concept, just to underline that. And there is, I think in the case of data markets, in addition to these different mechanisms that I mentioned, data value for the seller is very difficult to quantify. So if you are giving your data, how much you should ask for it, the price is a very difficult concept. And we need to go beyond the forecasting use case. If we just center the data markets on forecasting, there is not a big value on that, justifies all this research and effort in implementing it. So we need to find other use cases where data sharing is relevant in the energy sector and in the renewable energy sector in particular, and there is other use cases to do this. And this is aligned with these EU initiatives. Gaia-X officially is not a EU initiative, but it's now transversal to multiple European countries that are working on this common infrastructure for sharing data and common data spaces. So it's officially an EU initiative from the single digital market, and basically is to build a common data space where all the sectors can exchange data. And for example, in the case of renewable energy, we can vertically share data along the value chain of renewable generation, from the power plant owners down to the service providers on maintenance, forecasting, and so on. Okay, so, and then I end my presentation. So we still have time for some questions. First, ladies first.
Thank you. Thank you, Ricardo, for the presentation. In the first application for learning, and there's just, for example, one regression model, and the multiple farms collaborate on determining the coefficients, for example, the coefficients of the explanatory variables. Is that right?
Yeah. And
they do this based on their own local informed data, historical data. So in this application, the data are not shared. So they just announce the coefficient.
Yeah. Even not the coefficients. Everything is private. So if you want to make a forecast, you only are the only one who knows the coefficient. You multiply by the data you have, and then for the forecasting phase, you send upstream all the data combined with coefficients. Otherwise, it would not be private. And we combine everything: weather predictions. You can even have weather predictions from different vendors. Everything in the same model. And we apply these to all the vast wind turbines in North America, which is quite big geographical area, let's say. And it's computationally very efficient, and it's doable by a single model.
But there's another insight for the monitors
No.
like the data, just the collaborative analysis.
Yeah. But we can merge both data markets and safety learning.
Exactly.
Yeah, when you show the social benefit maximization, it was a standard demand and supply and demand function, which was interesting. So your models are actually very, let's say it's fairly complex. It goes through a lot, but when it comes to the social side, it's still there. Are there being work done on changing those objective functions on the social side, so each coefficient now represents a scenario of what is known as good or justice and things like that? Are there enough work done there?
Yeah, on the buyer's gain, it's if we go to electricity market, you have a penalty function for the market, the imbalances you have, and you can just plug in that function there. Seller's loss, no, and seller's loss is actually a big problem, because seller's loss is you have your own data, I'm buying it, and you have to know how much you ask for it. And no one has this idea. No, for that we have a parametric function that is related with the coefficient of the model we have, in this case the forecasting model, but it's let's say, speculation, if at the best, because it's a parametric. It's not people.
What are the
realizing.
scenarios?
Yeah.
What if this happens?
Yeah, but the research on that it's very low, and it is at some point is even philosophical about that. Okay, let's start with one. Then we'll take the last two.
Thank you for that. That's very cool. Because in talking to me, do you have a sense that buyers' willingness to pay versus sellers' expectation of funds actually match up? In my experience, buyers kind of want to pay as little as possible, and there's lots of cheap data out there, so that can set that up as well. For sellers to be quite happy about sharing data, even anonymously. And I'm curious whether the actual market those two things currently sync up.
It's a good point, because if you don't have some kind of equilibrium, it will converge to zero price or the maximum one. Here, the fact that you get data in a quality that is proportional to how much you are willing to pay solves somehow that problem. Because if you are a buyer and you say almost zero, I pay for that data, you get data with a lot of noise, so the value of data to you is lower. So in the next time, you are willing to pay more. Here, the way this works, like social welfare maximization, the same, because they can even put the maximum price if they really want data. They can put it at a very high price, and in the maximum to converge to that. So this is like the electricity market. The only thing here is electricity. We all need that. So it's like a primary commodity. We are willing to pay any price for it. And we are living times where we actually seeing that. In data, no. So it might happen you are not willing to pay any price to get data. And this might be a challenge for the maximum minimum price. That's why these models have advantages and disadvantages. So this is not the best one, and the other one is also not the best one, and the others are not the best one. So there is no optimal model. All of them have failed. Corinna?
Yeah, you were talking about use cases, and I'm just wondering. I think the model that you developed here is very useful, but if we look upon, let's say, a broader perspective, then there is a lot of data missing for many applications. Like there are countries like in Ireland where the wind farms have to deliver data to the system operator, but it's the system operator that can use it, and they are forecasters, but others that are now working in the market cannot improve their forecasts because these data are not available. And so that would be a case like in other countries, no data is available to anybody unless you are working with the wind farms directly. So, but by putting this into just a model that I can use this model and configure, I think you are limiting the use because I think and making such data anonymous so it can be used in all sorts of applications. That's where I think we have to go and have policies and work on national and international and or at least EU level or US level or China level, where we find ways that you can access data that exists. Like the meteorological community has that. We have a network where all the med centers can get all the data that they want, and they can work with that. And I think this is maybe where the use case that we should use, that we need to have the data available anonymous, but so that any kind of application can make use of it.
Yeah, I think what you are saying is more, it's what the Commission is trying to push with the common data spaces and GaiaX. So what they are doing is to have a new model for data governance so that you can tell this is TSOs in Europe, all the TSOs in Europe are allowed to get this data, whether centers, they are allowed to share this data with the community. So they have this common data space where you share data about climate change, climate impact, and so on. So they are trying to do this. There is actually some European projects, we are in one, that are addressing this for the energy sector. And the use case they have there for renewable energy is actually on share data about the wind turbine operation, all the internal data of the wind turbine across the value chain. So you can have components manufacturers improving their components because they have data of operation of a component for 20 years in one wind farm. So these also benefit everyone. So it's a question of generating, I think, benefits, common benefits by sharing common data, openly or paying for it. That might be a model Copenhagen city in the past had a data market that it's no longer operating because the model was not designed in terms of how you define the price of data. That's the key challenge. Okay, one last question.
As a data scientist, you look at the forecast model. You try to find the right model for the data account, for the combination of data. So what you do is you try to look into data, store and from the combined data. I was wondering how that works with your approach.
Yeah.
Like the human interaction with data, which still requires from you, don't go full into deep learning.
No, we use lasso as a penalty function, but not the traditional lasso penalty. In the past, we published a paper, I didn't mention here, but we explore different lasso structures, different sparsity structures, so that you can make an automatic selection of the features, which is very relevant if instead of 60 wind turbines, we're talking about 6,000. You need something that is automatic, because when the scale increases, even for human, is impossible to include any knowledge. And lasso works pretty well. Actually, we are here moving away from any deep learning or nothing. So we are not using any neural network, anything, just linear models. On the top of linear models, lasso make this selection of input variables. And then we are doing non-linear relations with splines and kind of parametric function, which is different from what we see in the literature. Even difficult to convince students nowadays to work on this, because they are formatted for deep learning and so on. So they are not very enthusiastic about working with linear models. But the fact is that they not only work, that we apply these to smart grids to control of energy resources in smart grids by using exactly this privacy property. It's a different role.
So you're saying there's no need to interact with data anymore?
Yeah, with this approach, you can make an interpretation of the model. That's also the advantage. You can make it everything automatically, then you give to the human the coefficient matrix, and then you can put some domain knowledge. But interpretability here is not only feasible, it's pretty clear for a human to analyze the model in the end. If it is like a deep learning, it's still a black box. Okay, so we can take some more questions. We have a discussion in the end, so we can now go to Paul.
Is it in your
Yeah, let me check. Is that difficult? That's what he always says. That's you there. Yes. So yeah, that was 4:30 yesterday. Why don't we take those?
Super. Okay, good morning, everybody. So my name is Paul Cuffe. I'm an assistant professor here in the School of Electrical and Electronic Engineering in UCD, which is just over that direction. And I want to present today on a topic which I don't claim to be an expert in. I'm talking about forecasting and hedging. And I don't know much about either of those things. Fortunately, I'm joined by my PhD student, Madia, who's just coming to the end of her studies here, who knows a great deal more about these topics than I do. But we've been exploring them for the last few years through this lens of prediction markets. Okay, so it was just pure curiosity on my behalf. Like, one of my favorite facts, like one of the coolest things I ever found in the literature is that if you have a database of 10 million horse races, you know, and such databases do exist, and you come back through that, and you can look at the bookies' odds for each horse starting that race. You know, so horses that are given by the bookies, you know, chance of 5 to 1 to win the race, you can convert that to an implied probability. So you can look through your database and find that set of horses which were given an implied probability of 12% of winning the race. And it turns out that such horses really do win 12% of the time. So, like, this seems under-commented, right? That humanity has evolved its way to having this very powerful oracle, like this really good way of divining the future. And all we do with it is like silly stuff, like figure out which horse is going to run the fastest. Like, it's kind of bizarre. Like, there's a lot of important things that I actually care about. Like, it annoyed me greatly. It annoyed me greatly during COVID that, you know, you would be trying to plan something, right? God help us, loads of people might be trying to plan a wedding or something, and to be sitting there in the depths of lockdown saying, you know, will I be able to hold a wedding in May 2022, right? And all you can do is different experts have different opinions, right? You know, not at all actionable information, right? Whereas if there was a betting market, right, with actual money changing hands, phrased on the question, will it be possible to hold a wedding in Ireland in May 2022? Then you could look at the price in that betting market, and it would tell you, how likely it is that you can do that thing. So that was a frustration, right? Similarly, it's frustrating now. Like, will there be blackouts in Europe this winter? Who knows? Big room full of experts. We can all just sort of have vague opinions. But if you actually want to put your hand on an actual number and say, there it is, there's the consensus position, you can't do it, right? So this is kind of my ideological belief that liquid prediction markets are a powerful and underused tool. So this project is just a little kind of way to point that out in the specific context of the renewable energy industry. So where it came from is a broader project, started back in 2017, kind of looking at ways that blockchain might be relevant for renewable energy. So the thread of it here is myself and Madia. My photo was taken just over there in the corner of the lake on a much sunnier day. In 2017, it seemed like blockchain was going to be the thing that was going to unleash prediction markets. And for whatever reason, government interference or something, centralized prediction markets didn't quite take off. In 2017, there was a lot of talk that your blockchain hosted platforms would crack this. I don't know that that's happened. I don't know whether it will happen, but it's sort of immaterial because the way that the research has progressed, we're kind of platform agnostic. So Ricardo was just talking about data markets. I suppose prediction markets are kind of closely related, but they're kind of just another step forward. It's a crowdsourcing method. It's gathering data from various sources. It's gathering beliefs from various sources, and it's a mechanism that rewards accurate belief and punishes false belief. Right? So betting markets are a tax on foolishness. And so if I feel that I have some useful information that bears on a question, that I have good reason to believe that there will be blackouts this winter, and I look at the price in the betting markets that doesn't seem to reflect that data, I go, aha, like an opportunity has opened up for me here. Like there's a mispricing in the market, and I can take my particular belief or data points and I can go in and I can profit on that mispricing, right? But in profiting on the mispricing, I arbitrage it away, right? I end up moving the price of the market, right? So that's the idea. That's why the market will always impound all the information. Okay, so there's different ways you could structure these markets. And again, it's just going to depend on what it is that you're trying to forecast. So just again, to kind of repeat it, the key features that we have here is that we're dealing with some uncertain future event, but that will close, okay? So the market will close on some date. There'll be a settlement question that can be checked. So did that horse win the race? Okay, we made it to the 31st of March. Was there a blackout in Europe that affected more than 1 million people? There has to be a close, right? And furthermore, we can continually trade shares in this. So I can buy a yes on that, or I can buy a no on that, if it's a simple binary prediction market. So if I buy a yes and we get to the 31st of March, and indeed there was a blackout, I can redeem that token, that contract, that option. I redeem it and I get €1. If the thing hasn't happened, I get nothing, okay? So to hold one of them, you would never pay more than €1. To hold something whose max payoff is €1, and you never pay less than 0. So the price is going to fluctuate between 0 and €1, and that can be interpreted as the percentage probability of it happening. Okay, you'd only pay €1 to hold such a thing if you were certain. So that fluctuating real-time market price is a view on the consensus of how likely the uncertain future thing is to happen. This is some of the backdrop in a centralized platform. So a bookmakers, you are trusting that bookmakers will honor their commitments. So Paddy Power and Betfair are owned by a company called Flutter, who have their headquarters. There's an office park as part of the Belfield campus here. Just over that way, there's some like 8,000 people in there settling and coming up with prices for all the Paddy Power's betting markets. The idea was that blockchain would disrupt this. Instead, you would have smart contracts. There would be no central authority. There'd be no intermediary. You would somehow, you would buy a token, a blockchain token, and some smart contract wizardry would happen and figure out if the event settled one way or the other, and you could redeem that token. So there was several projects like this. They were pretty attention grabbing a few years ago. Augur was one of the bigger ones. And again, it's a platform like this that you come in. So this is a bit historic. Will Donald Trump win the 2020 election? And you can take a position on that. And the idea is that once you've taken that position, you now have a blockchain token. So no matter what happens, whatever your government does, if a law gets passed, you hold that blockchain token, which should redeem. So what can we do with this for the topic of today? We're trying to forecast wind energy output, let's say. Like I say, I'm no expert on forecasting techniques. All I can say is that there's a lot of them, right? You could almost cynically say it's an infinitely fertile source of research questions, okay? Like you'll always be able to come along and say, well, we set up our neural network in a somewhat different way, and we did this, and we ran it like that, and then we got this MAPE value, and it was a little bit less than what someone else got 3 weeks ago. So, everyone can play this game forever, right? I just wanted to dive in and say prediction markets are a way to referee this, or to abstract it away, or make it someone else's problem. Okay, like I said, I know nothing about horses. I don't know one end of a horse from the other, right? I've never ridden a horse, okay? I'm not a very horsey person. But if you ask me, like, who is going to win in the 3:15 in Aintree on Thursday, I can tell you, because I just have to go and look at the bookies' odds, and it will be there, crystal clear. Any fool can figure it out. So the idea here is that all the clever forecasting people, you people, can take positions in prediction markets, and then a system operator, whoever it is, can just look at the consensus, look at where that arrives at, and without needing to know much, can know they've got a good answer. So with this paper, we were trying to show that. It's a pretty hard thing to simulate, or you'd almost say an impossible thing to simulate, because there's a magical black boxy nature to the doings of a market. I mean, if I could peer into the mind of a market, I'd be very, very rich. So it's sort of hard to write a paper that shows the magic of what the market is at. But all the same, we tried to do it. So we're just trying to show kind of as a showcase that you can have different agents that would have different subjective beliefs about what the wind forecast should be. And that then if they trade in a prediction market, the price in that prediction market will converge to a useful forecast. So in that, we had to do a bit of simulation of the market maker. It was assuming that there was a liquidity provider in the middle of this that people could bet with. So someone could come along wanting to do an order. So to take a number of shares at a certain price. Similarly, after that order has been fulfilled, that will move the price in that market. So that's what this second equation here is telling us. There's assumptions that we embed in how that market is being run. Like essentially, this is the stuff that gets baked into those fancy blockchain prediction markets. Okay, so somewhere deep within Augur, there's something like this happening to figure out how you can trade with the liquidity provider. So we sort of set up that's one way of modeling what's happening in a prediction market in the center of it. We also made assumptions about each agent has a belief about where the wind price is going to go, and they're trying to maximize their utility by taking a position on that. And so that was their problem, right? So we could simulate rounds of this, that their beliefs are evolving over time. They're trading in and out of that market, and the market price is ultimately updating until it reaches a certain point. So it's a case study. It's just an example. It just sort of draws out a discussion. So here we could say, if we had a prediction market that was asking this question, in a particular day, will the peak renewable generation be less than 80 megawatts in Ireland? We could simulate different agents that had different forecasting techniques for that. Maddie, what were the forecasting techniques used?
The agents, one of them, Kariniotakis, one of them, Bessa, physics model, and one of the Gaussian process.
Yeah, so it was three, classic kind of forecasting techniques, and you could say each of those agents will run their model, make their prediction, have a subjective belief about how likely this settlement question is to happen. Then they can trade in the market because they're trying to maximize their social wealth, their own welfare, given that belief. And you can see that the market eventually settles down to this position. So the market in that case believes that there's a 56.4% chance that the renewables will be more than that. There's a way you could actually, you don't just get a spot forecast. If you look at the order book, right, so it's not just the price that the last share changed hands at. You can look at the full order book, and you can actually look at the market's belief as a probability distribution. So you get extra data out, which is another nice bonus with these techniques. So that paper was just to kind of showcase what we're talking about. This paper here goes a little further and says we can actually get to a position where if liquid prediction markets exist, and I'm selling into an energy market, I can use them as a hedge. So I can be hedging off my risk exposure of an underproduction or an overproduction by taking the appropriate position in a prediction market. So in this paper, we outline one way that someone could do that. But what we're trying to get at, I think it's the more kind of fundamental point, is there's something really cool that you set up this tool that a wind farmer can say, cool, I can now hedge my risk. So that's just a nice tool for the wind farmer. But as a kind of externality of that, as a side effect, you're also getting this really good forecast of what the imbalance is going to be tomorrow. So, so we lay out here how you would do it. You're basically taking opposite positions. So we're assuming you're participating in a market where you get punished for not operating as you bid. And so if you overproduce or underproduce, you get punished. So the way I would hedge that is if I bet against what I think I'm not going to do. So I'm participating here in the electricity market. Then it's the balancing market where I'm worried that I'm going to get punished. So I hedge what I'm doing in the balancing market with the appropriate position in prediction markets, and the combined payoff of those two is my hedged revenue. So I'm hedging my imbalance costs is the best way to put it. So this is basically how I get punished. There's imbalance prices that are set. So for every megawatt more that I produce, or every megawatt that I don't produce, we can quantify how much that costs me based on what I bid I would do in the day ahead market. In the prediction market, similarly, I could take a long or a short position. So if I committed to producing 50 megawatts, I can bet that I'm going to be long that, or I can bet that I'm going to be short that, and we can figure out what my payoff is going to be if that in fact happens. And so we show in the paper, at considerable detail, done fabulously by Madia, that if you follow the trading strategy that's laid out in that paper, you can hedge your exposure here, so that your revenues, you have less upside and you have less downside. Okay, so your combined revenues are nicely hedged. So perhaps that's not surprising. Okay, we all know that hedging exists, but it's cool that you can hedge like that. And as a bonus, by participating in that prediction market, you're generating useful information for wider society about what's actually going to happen with how much wind there's going to be. So just with those two papers, it's trying to tell a story about the power of prediction markets. We hope that we've said they can benefit wider society, power system operators, by giving really good forecasts. They benefit the producers by offering hedging. And it just seems, like an easy way to harness an existing technology. So there's future stuff you could do with this. Again, we feel we're only scraping the surface. There's not much literature on this in power systems. So we're really just scraping the surface as, just curious people trying to work our way in. You could come up with lots more bidding strategies. We did that coordination with the balancing market, but there's lots more markets, lots more ways you could do that strategy. You could look at the iteration. If someone has a good model for forecasting wind, can it actually take in the prices from the market and iterate like that? So lots more can be done. So thank you.
We can take some questions for the discussion.
One way of hedging for renewable power producers could also be if they exceed their production, just to turn down production. Is that somehow taken into account in that model, or is that just working financially?
It's financial, right, Madia? But do you want to come up here actually, Madia?
Thank you for your question. I think you're asking about the overproduction case, which in power producers usually have curtailment coverages, and they curtail. Actually, this hedging method mostly applicable in underproduction, which will be penalties for underproduction case. In overproduction case, usually you get if the wind power not curtail its power, they will be compensated with a price which is less than the day ahead market price. So it means like a loss of opportunity. So hedging is not, it does not mean that in that way. Yeah, and that's why we actually it's the important point that we mentioned in the paper that we just considered the overproduction case. Maybe in some regulation markets, important wanted to show that the symmetry of the approach. If you are in a market mechanism, if there is a penalty for overproduction case, be hedged through the long shares, and if in prediction markets, and if it's an exposure of short underproduction, then you buy short shares in prediction markets. So there is a symmetry between those. But as you said, in overproduction case, does not really usually matter. Prices they curtail or they get the price just less than.
So, brief question. So, all these data given in the previous presentation, so there's an aspect of stochasticity that's in one direction and non-linearity in the other direction, and the interplay is important within the time scale that we're looking at. These models that you presented, it looks like that you have to take a time scale which kind of provides some sort of stationarity in the process. And with non-stationarity that, like alignment with the market that you presented, it'll be hard. And if you make it liquid, most people do not have these very specific, tools to look into interaction between stochasticity and non-linearity. So what are your comments around? Because you have to be the common wisdom, right, for this to work.
Yeah, sure. Actually, it depends on the local model of the participants in the prediction market. And the prediction will just aggregate the forecast coming from various sources, which in our case, there are some, as I said, for example, in our case study, we consider 3 models. So if you're talking about that, the distribution of the renewable, for example, wind power, and we know that they are not stationary. As we said, it was reflected in the local prediction models of the agents. So, for example, one agent doesn't consider this point, and so there's less accuracy in their model, and one of them does that. So when they both compete in the prediction market, that's the beauty of this model. We are saying that the final aggregated results is more accurate than this individual ones. So this considering this point depends on the local models of the agent. Maybe they consider it, maybe they don't. But the prediction, the point here, we are saying that prediction market aggregate these results in a more accurate way. But
if you aggregate them, how will it?
No, it doesn't deal with the stationary.
Yeah.
It does.
Yeah.
And also, like, the whole question of whether you would get the liquidity in these markets is just something we haven't looked at, right? That's
That's
Yeah, I mean, that was my question. Wouldn't the accuracy of the resulting probability prediction depend upon how thinly traded the market is? So if you had a thinly traded market, it might be mispriced, or it would be inefficient, basically. But how would you quantify that as to how well the prediction might represent the actual probability when you'll have variations in volume in the market?
It's a huge question, and it's something that, like I say, it felt for me at least, Maddie might have a different view, that this project has just been, scraping the surface curiously. And, we're trying to do things by pointing out, oh, hey, there's a win for both sides here. There's lots of wind farmers that want to hedge. So they have an incentive to do that. There's a reason people should participate in these markets. That was in some kind of loose way to address this idea of where will the liquidity come from. There's a much bigger kind of question in economics about, in general, how efficient are markets? Like you're saying, if you've got a mispricing in the market, the idea is that if it's an overt or obvious mispricing, people don't leave money on the table. So, the idea is that if it's a market that anyone can participate in, this was part of the blockchain piece as well. That anyone anywhere in the world can come along and spot that mispricing and come in and fix it by trading. But how realistic that is, or how much that models the real case, I couldn't possibly say. Maddie, do you have anything to add to that?
Mispricing due to lack of liquidity is a general problem in prediction market. Yeah, you're just considering a case that if we have different models and if we have a liquid prediction market, how it aggregates the results. But that's how it is.
Two more questions only. Sorry, there was.
Okay.
There's a lot of questions.
How do you compare the benefits you get with standard methods in the literature that combine forecasts? Because the baseline today in applications, at least in industrial applications, is not really individual forecasts. As we saw also from the presentation of yesterday, and users use different sources of forecasts and they combine them with combination models, and this is state of the art.
That's a very good question. Actually, aggregating through prediction market is comparable and combined approaches in the literature, as you said, they combine the PDFs. For example, it's not comparable with, for example, yesterday's session ensemble NWP, which they run the fiscal model several times, different initial conditions and parameters, and get the distribution. So I just wanted to clarify this. But as you said, it's comparable to the combined PDF models, and yes, in the paper we have compared it with, for example, weighted combinations of the PDFs. And there was a slight improvement. I'm not saying there was a large difference, but the slight improvement, and also another benefit that is they mathematically develop a weighted combination of them, which will be very mathematically complex when we are really combining a lot of models. But in prediction market, since it's a market-driven approach, so it can combine a lot of models. So one of the maybe it's not improvement, not a numerical, so much numerical improvement, but in the approach that we can aggregate more models. So that's what.
Question.
Just in terms of pricing, do you foresee it will operate independent of the hedging financing market, or do you see it be discounted financing market, or have you a feeling for where the pricing may go?
Pricing in prediction market is a totally separate financial venue. Doesn't have anything to do with the physical electricity market or anything. It's separate financial. It's just in the hedging application that combine the revenue. It's like hedging application financial markets. For example, you can think of it as a financial derivative. It's a future market. But it's separated from the electricity market. But since the payoff in two markets, we realize that the payoff in two markets depends on the actual outcome of the renewable power. So if the wind power participate in both markets, the combined revenue will be having a more predictable way, lower risk, meaning that, for example, lower standard deviation, something like that. But it's totally just like a financial derivative.
Okay, so it would be really down to participation in that future market. And the money that's in it, the values come back. Pricing that the way it's set.
The pricing in the prediction market,
Yeah.
just depends on the liquidity in the prediction market. It can be settled in two ways. For example, in the first application for testing, considered an automated market maker. It can be based on market making, or it can be just continuous double auction. Each orders when bid and ask offers will be placed on the order books, and trades will be filled when two opposite trades match each other. Which in this type of market, in terms of liquidity, continuous double auction has less liquidity than market makers. For example, in case of other problem of liquidity.
There was Brad.
Yeah, I was wondering with respect with you said you're not looking into, or it has to be separated from the electricity market. Yesterday we heard this example where everybody is using the same kind of forecast, and that actually generates huge imbalance and in that sense cost. So how can your energy or your markets principle help on that, because this is, I think, a huge problem that we have the correlated errors, and there you would imagine that if the market can solve it, as you said, or you had derived in your paper, then it should also be able to solve that, because this is a real problem. I mean, if you realize that everybody is doing the same and there is a good chance that this is not going to happen, how can you how can you avoid the convergence of everybody else? Yeah.
Actually, yes, I get your point. It's very interesting. And the thing is, as I said, everybody with similar data and similar. For example, when they all know that there's gonna be rain tomorrow, no one gets nothing raining. Yeah, that's the point. Of
But
even
if I'm sure that I
electricity
think
market.
it's not gonna
Yeah.
rain tomorrow, so how can I change
Yeah.
that?
Yeah, actually, the thing is, based on the forecast, they submit a bid in electricity market, which will be an exposure of real-time imbalance costs, and then they buy short shares in prediction market. So as I said, there's gonna be financial loss in prediction market as well, and there's gonna be imbalance of electricity market as well. But since the position offset each other, and we are not saying that we are removing the risk, the revenue just be in narrow range. We are just saying that. The CDS, I didn't show it in this slide, but the CDS shows lower standard deviation. Just here, but we are not removing the risk yet. There's gonna be risk in prediction market and there's gonna be risk in the last. We're just narrowing the range and reducing the risk measure.
So, Brett, make the last question.
Somewhat of a different topic. Did you consider behavior like bad actors and various actors in the market?
Very good point. We get it from every reviewer of each paper. Yeah.
I wasn't one of them. So.
That's really important and matters. Some of the prediction markets shut down by the governments. For example, the one we had in Ireland. Because it's concept they could have because of the betting actions, gambling behaviors, and legal and societal concerns really matters, and that's why there are limitations on the amount of money they can be traded in these markets. Yeah, it's very important, and one of the important limitations of prediction market in all the for renewables for any type of application. And you're just saying that in a market, technically for renewable application, at least when we have some, for example, a crowd consisting of data owners, forecast providers, researchers, experts, we can limit that this type of participants, which trade based on the statistical models or any type of models, and they are we consider that as an assumption in our work that there are rational agents who just want to maximize their utility functions based on their beliefs. So in case that there are irrational agents and some bad actors, as I said, there's going to be this other reasons for mispricing. Yeah, it's an important problem.
Okay, so there was 20 minutes for discussion, but I think if you want to keep this on time, you can have the coffee break because we already have the discussion. It was a very rich questions and presentation. From this session, we can close it now. And I'll make coffee break. Yeah.
As is traditional with this, no, that's the afternoon session. Actually, we're a few minutes late, but I'm not sure whether we need the full 1.5 hours for the open space session here, because we already know, most of us already know what to do. So we just convene 10 minutes later here. So for the open space session, we've seen that we have a lot of interesting topics here. We've seen some of the new things that are coming up in the near future and maybe far future. We probably brought some ideas from home that we also wanted to have. And so I don't have a particular slide for it, but we're going to have an open space session on research gaps. So what should be the research plans for the next probably 7 years or so, because this task is 4 years. We're 3/4 of a year into the task already, into that phase. And there's a relatively easy extension of that task for another 4 years. So probably this research gap analysis would stick around another 7 years or so. And in my view, one of the main reasons why we should have that research gap and research center is to be able to point to this as this is what the common knowledge, what the integrated brains of the IEA task of notionally the largest discussion group in short-term prediction worldwide has come up with as some of the topics that we should address. Then you can go to your national funding organizations and say, my idea here is on this list. Internationally, it's seen as a good idea to do that. Please give me money. Sometimes that works, sometimes it doesn't. That's sort of one of the really in-hand reasons for that kind of an agenda. The other thing is just inspiring research, because often you have master students that could be interested in getting some position somewhere or some topic somewhere that then can revert to that research agenda and see, okay, this might be interesting. If you're still thinking back, you might even know who proposed that and can collaborate with them and similar. For the industry, it might be a bit of a different incentive to be here. That's because academia wants to do projects, wants to do research projects. Industry wants to have the results of those research projects, but if we don't know what is really needed, what is really important, then of course it would be difficult to do. So, having said that, we try to have it here in 3 different stations. One, and of course we could have done it according to applications, trading, PSOs, someone else. But another possibility was to just go at the timelines. And since it's open space, move around like you've seen yesterday. I had a station here, and I think I saw nearly all of you coming around to that station. So you can just go around and come with input to the individual places. So what should be the next bigger research topics for minute and hour scale forecasting, for intraday and day ahead forecasting, and for sort of several days to seasons forecasting? We'll make 3 stations, and I don't think I have actually talked about anyone who's managing those stations, but I would be the one for the intraday and day ahead. I would put here.
The minute you want.
Yeah, Vikram will do the minute forecasting, which we put there, and then we have one more here on that.
I have forgotten story.
Whatever. Let's start with the minute scale forecasting.
Okay. I should be summarizing it, right?
Yes, exactly.
So I have the.
You can also go individually.
No. I'll just summarize it briefly, and I'm pretty sure I will not be perfectly representing, your interests. So just stop me and say like, hey, Vikram, just try not to use unparliamentary words. So what we went through is like the first thing that that was the most important thing to me is like almost no one spoke about
here is a new algorithm, here's a new method, here's a better method to get more accuracy. That no one, not in terms of time series, deep learning, that learning, none of that. The entire thing was about the quality of data, the clarity of data, the clarity of understanding what the results mean, the interpretation, the interoperability, and every time something new in terms of technology or methods came in, where are the benchmarks? We're sorely missing a lot of benchmarks, and we're sorely missing a lot of guidelines and recommendations, and ultimately standardization. So I think that's something we really need to look forward to this. You will see that here we have a lot of ideas around minute data, a little less on our data, but as a second thought, I put in here what are the connections or all other business. And that took pretty much the maximum amount. So a lot of work is really around that connecting piece from what are the benefits and things like that. We did have a chat about benefits. It's still guided pretty much mainly by finances and market and prices, but there is an opportunity to look at slightly wider aspects, like social aspects or social benefits, but that's something that's so high level at this point. I don't think we should go into that right now, at least in this meeting, while keeping our like that window. I'll take a couple of more minutes just to say what we're looking at. The ideas that came out from the minute data, as I see, is the robustness of missing data and the good quality of missing data, better information about when it cuts off and things like that. There are questions on the possibility of having NWB data on minute scale. Is it possible at all? Then error propagation on very short time scales, and also the mesoscale phenomena, sharing of such minute data, how and how much, to what extent, why, all of that. Then some questions around technology. There was certain things, questions on LiDARs, and then this technology I know nothing about, so I'm just reading it out. It's called radio occultation. Yeah, okay. And then there were some questions on skycams that came from Gorka. And then also, if possible, like a dense network of high resolution of pressure information and scale changes. So information on different scales. There was a point made by Jethro on using minute data, the importance of it in ancillary services, and 1 minute data, information needed up to an hour ahead. And also from him, where reliability driven rather than demand driven estimates, where do they stand in terms of benefits? And also on, again from Jethro, on joint prediction and production of prices rather than individual. And then there was some questions at the end was around the use of air density and temperature and humidity better for these very short-term forecasts. That kind of wraps up the minute data information. Coming to the hourly data, there was less questions around it, but sudden questions on detecting sudden stick changes. That was actually the first idea we discussed today from Liam. So how to adapt quickly and organically and fast, but we haven't seen it yet to a certain extent. There was questions on or ideas on crowdsourcing of data. In fact, we'll come back to it again in the other businesses. Again, NWP demands on, again, hourly data and the quality of it that came up. There was some question on offshore and the need of assessing rapid ramps using other technologies as well, including LiDAR, and to what extent we can know, like, I mean, we typically know these ramps apparently about 5 minutes before it's good enough, but how much can we push it? Can we even push it for an hour before with hourly data, or do we need to go for smaller resolutions? And then again, can we make NWP models better suited to dispersiveness? So these are the questions that came out in the hourly data. Coming last to the connection and the other businesses, there were lots of ideas. So mainly this was about the quality and the interpretation of data. So one was, again from David, came in on ensemble member tracking and keep record of the previous perturbations and go back and see what works the best so that we don't put in perturbations randomly, but more selectively. Then ensemble member weighting, and all are treated equally right now, but we can do more and come up with some weighting aspects of them. And again, a lot came from David, so unless I'm not saying the name, it came from David, okay? He's the OG. And then there's also some questions, I actually put it on that, like what about the downtime classification and detection? So it's good for like turbine owners, not that much for the TSOs and operators. So it is being driven by money. Although there was some question around aspects around, yes, we would like to know if the downtime will be for 30 minutes, for 4 hours, or like days and things like that. Also on minute or hour data, what are the highest and the lowest possibilities and the metrics to evaluate them? That came up, and I put in a question towards the end, and it was kind of taken well, so I stuck it in, that a lot of these definitions and terms and semantics, the same word means different things to different people, and different words mean the same thing. So how to avoid this Tower of Babel kind of situation? We need some guidelines and clear practices on how to interpret what does a word mean, what does the word skill mean, what does error mean, and those things. So that also, we had a lot of chat around standardizing even database presentation, the metadata that's needed, and the quality of the data presented, how to assess the quality. Kathryn spoke about the explainability of data, and that was quite important because that's missing in many ways. She also spoke about the speed of data. I mean, you're just getting more and more and more. How to go for reduction, parameter reduction, model order reduction. How much do you need and what can you ignore? Then from Liam, it was on data transmission. What's the most important data to transmit? And that was another question. I also spoke about the transferability of some of these things, like you get some result from one turbine, and then to what extent and how much can we use it for other farms and things like that. There's always a hiccup around that. Do we have benchmarks? Then I think I also said something about some kind of a benchmark on the error reporting and formats, and Caroline agreed that yes, benchmarks are needed. Again, I'm repeating myself for the 10th time. I think that everyone thinks their model is the best, others is the second best. But unless we have a uniformity of that reporting, we won't know how to fairly compare errors, and the intercomparison will be missing. Then the connectivity of resolution was a question. For a given question, is 1 minute, 5 minutes, 15 minutes, an hour, what's the most relevant question? Based on that, your best model would come in. And there can be many. Some are relevant, some features are not, some models are not. Which ones are legit and which ones are not relevant? That was important. The only linkage we found with other bodies was for possible repowering of farms where the actual mechanical or structural aspects would limit the amount of power it can generate in a second round. It's like crop, for example, in the field. So we have to think about that. There was some question, Caroline, on can we combine this with solar and other kind of resources, and we can look into other IEA tasks. There are also some EU tasks. I think I said there's the Moderner Lands cost action right now on renewable energy islands. They're trying to define it from a very high level, but that's the direction people are moving towards. And then David said something about there is a forecast horizon skills assessment, after which we kind of ignore and where the skill drops off. But there was a question on, again, what do you mean by skills? And again, it came back to some of the definition, how we interpret it, define it. Based on that, everything's going to change. And finally, Michelle came back with a very solid example. And I was also saying that some of these questions can be taken up by funding that's there right now, or even there are options. But in terms of crowdsourcing, Michelle's point was like, even if we can get some of the primary schools to agree on putting in some cheap equipment around the country, that would create a dense network. And we can look into it and these kind of things. That completes my summary for all these things. And we'll make a little report hopefully out of it, which will represent your interests. And if I misspoke, just correct me now or later.
Thanks, Vikram. For the intraday, they had actually we had in part a few of the things that actually were kind of similar. But we also had some sort of low-hanging fruits that aren't really research topics, but more things that would be nice to have for the operational forecasters, like 100-meter data of a lot of different quantities as a standard output in essentially all the numerical weather prediction models we have. Open numerical weather prediction data, not only in Europe or in the US, but also everywhere. Data quality and quantity is important, and also a solid and ideally standardized metadata description of what is really in that stream. If I get something with a flag of 3, what does that 3 actually mean? Then there was still some on ensemble forecasting, where model management and combination was one of the things. How to combine different ensembles also with different timing. EMI, for example, in Denmark is now having a new type of ensemble that has 12 members, but they run 2 members every hour. And so after 6 hours, they actually have a complete ensemble set renewed. How do you deal with that? Is that sort of the same like the old ones, or do you just run that every time again? And of course, if you have GFS and ECWF, then they come at different times. How do you combine those? Smart post-processing of local weather was one of the things that could be helpful in the future. More particular meteorology topics were high frequency variability in the tropics, like some squalls that can be only 3 hours and give you full wind speeds for a short time period, where the global models only say you got 20%. Or low-level jets, including how they break down in the morning, how and when, how that exactly works. Use of some of the PHI data from satellites in the numerical weather prediction model. Variable grid numerical weather prediction models, which is a bit of a problem if you do parameterizations and suddenly get a finite grid. How do these parameterizations actually have to change? And similar, and then there's also operational constraints. If you have a dynamically varying grid, then you don't perfectly know when your run actually is going to be completed, which for operational purposes also is a problem. And one of the major topics actually is still multivariate forecasting. So you have these ensembles, and you have a probabilistic forecast of wind power, which is nice, which we can do since quite a number of years. We have probabilistic forecasts of solar power. But if you combine those two just as two probabilistic distributions, you're probably not being right if you use that for another thing like a price forecast. So then you need to actually propagate everything. And I don't think we're there yet. Figuring out how that is done. The forecast from embedded generation. No, that one, the multivariate, also talks to integrated applications. So you get the full data stream, and you have to build particular applications. If you want to have a price forecast, then you need to get from the start to the end, all sort of in one at least conceptual way. Embedded generation was one thing. So behind the meter things that don't really measure separately. How do you get good training data for that? How do you parameterize new wind farms that might be embedded? And then there was a number of interesting things sort of on the use of artificial intelligence and machine learning. One was where to put the human in the loop. And the current example of this has to do with AI, because the current example from David was that currently the biggest skill of a forecaster is to know when the AI doesn't have skill. And so is any training to be done? The EASA, the European Agency for the Safety of Aviation, something like that, had a report on AI in aviation, and obviously aviation is more security conscious than the power system, or at least as security conscious as the power system. So learn from others how to employ AI for critical applications. And then again, David had an interesting idea on non-sample forecasting. Things that just cannot happen as sort of guardrails of your machine learning training. If your machine learning comes out with a wind speed of more than Mach 1, it's probably wrong. And you can catch that automatically. Then there might also be data sharing beyond just the energy sector. Mode S was one of the ideas that we had talked about for a while, and that some other providers already are assimilating that data from aircraft around. So you get a high observational density in 50 kilometers around airports. And the other one was potentially analyzing social media automatically for demand forecast. That could be a quite interesting topic. I think that was sort of most. Now, yeah, also AI and training. How far are we from the training set? Can we directly say if we have a prediction for how good my AI is based on how far I am from my training set in the next few hours? And that might be helpful for, I don't know, something which would probably need another bit of research on how to actually employ that. So I think got it. Yeah.
That's right. Although I think it's amazing how many interesting ideas come up. And one thing that I want to maybe start with, that I heard from Vikram and the discussions over there, is that a lot of the things that we discussed here, and that was one of the things that we also hear, is we need a recommended practice and about this standardization. And I want to just emphasize here, we have managed to have a recommended practice on solution selection, on how to make benchmarks on files, and how to use measurement data for all sorts of applications, and how to evaluate forecasts. And I think I can proudly say that it's going to be published by Elsevier in November, our first version, and it's going to be open access on an electronic basis, and then the book is of course available also to buy. And I think, and I want to emphasize that it's really important to spread that out to everybody, because it is, I find it's a milestone that we have reached in this group and forum here, to really get so many people to provide input and to have something that is also accepted by 20, have been accepted by 23 country representatives. We have also data communication kind of in there already, that is maybe on the first step, but it is still very useful information. If just the industry and everybody could adopt to that, we would really be on a new level, I think. And that's where I start here with the seasonal forecasting. That was also one of my questions. Do we need a recommended practice? Are there areas in the seasonal forecasting that are similar or that are very different? So that's one of the things that we should definitely discuss and in the next couple of years. Then just going kind of a little bit more into detail, we have also inspired by the recommended practice, probably also necessary to have a method of application, because there are different methods out there and there are different applications, and mapping and giving the industry an objective table or information source on which kind of applications or which methods can be used in this kind of application. Then again, also what are the appropriate metrics for evaluation? We have a good basis in the recommended practice, but that is mostly looking into the shorter terms. And that's of course also a question, do we need other evaluation methods? Then what are the sources of uncertainty and of the methods and their models? So it's again coming down to how do I evaluate, but also what are the uncertainties that are in the methodology, and do they cover the uncertainty, and which type of uncertainty do they cover? So if I provide a probability from an ensemble that has a different target horizon, then what my target horizon is for the seasonal forecasting, that can be challenging. So I need to know these limitations, and that's where we also said we have to have kind of a mapping, a table of what are these time horizons. Then who are the end users and the applications? That would be a useful topic to look into. What is out there, and where do we have some kind of experience that we can share with each other, and that we can make it easier for those that want to get into it. To where do I look? What should I actually take into account? We had the spatial aggregation and the intercorrelation assessment. So we want to have it on a grid point basis. Do we need areas like countries or jurisdictions in the power system? This kind of stuff that that also relates to the forecast skill. So a horizon assessment, what is available and on which time horizons, and what are the skills. So what kind of skill can I expect if I look for a seasonal forecast, or if I want to make decisions out of seasonal forecast. We had that's the probabilities of extremes. So of course in seasonal forecasting we have asked ourselves, do we have to look into different type of extremes? Are there correlated non-extremes that lead to extremes? So So the questions that we have already discussed a little bit yesterday, but then I'm just asking the questions, is there any difference in the timescales when we go on the seasonal forecasting, and how do we have to look upon extremes when it comes to the longer time horizon? We have also looked into operation and maintenance, or we have looked into what if we make a seasonal forecast and there is a maintenance, does that help us in saying when should I, when do I have to, when can I possibly, what are constraints also in system operation? We have 80% renewables on the system, and we have only 20% other, maybe more controllable generation. We don't want to have them to do maintenance on the generators when we know there is low wind or low solar generation in the next weeks. So this kind of planning. Is there a value in running interWP forecast or seasonal forecast, or in general, what kind of model should we actually use for seasonal forecast? Should this be the climate models? Should this be the numerical models? Should this be a new type of model that we are looking into? Because we are in the middle of two modeling types. The numerical models that have a very detailed schemes of the atmospheric lower surface, and then the climate models that make more assumptions to the lower surface. So we need a new type of model here, or can we combine them? Then we have looked into, are there actually data types that exist or do not exist yet that can help us improve the forecast? Oh, is there some water? Sorry. Yeah, so that was I think most of it. There's one really interesting discussion we had was how we deal with the ocean. So I mean, if the surface temperature of the ocean is wrong, we know also in the shorter scales that can make our results on the forecast very wrong. So how does that affect the seasonal forecast? How do we need to deal with the ocean? Also, maybe climate change, if the ocean becomes warmer, if it becomes warmer. Time resolution was one. Do we need, what kind of time resolutions do we need in the forecasting, but also in the output, in the input processing? And I think, yeah, one last thing maybe, this is the correlation effect of the variables that we definitely have to look into, because the seasonal forecast can give us a lot of value, but they can give us also misconception of what can happen or how things can develop if we only look on one variable, like for example wind speed, without looking on other variables affecting solar generation or hydropower or things like that. So I think that's about it, and I think it's a very interesting topics that we have, and I hope that we will get a few of you signing up with John as the work stream leader in bringing all this together and finding some topics that we a little bit deeper into, dive deeper into. So thanks for the really good discussion. It was very, very interesting.
Maybe the biggest problem with all this is
that's way too much. So instead of just putting a hand up for any of these topics now, we'll have to do some bigger effort in actually collecting that and making that accessible in some way. Maybe we can later on go towards some online survey of what people could be thinking was interesting with a lot of commenting options, and then get that as an input to the paper, because I don't think we can do much in terms of prioritizing right now. It's just too much, and this is just great because you did good, you did well, and I'm personally a bit overwhelmed by all that, but we'll get some message through it, and we'll get that sorted. We can start discussion over lunch.
A lot of data to areas where there is no methodological or very sparse data. So is this also something that WMO is opening up to kind of then also, as I said, there is a data share of observations, kind of, if this could come into some kind of policies?
Yeah.
Or is it only?
Yeah, absolutely. I mean, observations in WMO are probably the most important thing that are on Web3. So there is a whole commission on infrastructure, which is a much bigger group than the energy study group. And as you know, it also deals with some recommendations how to set up measurements so they can be comparable. So they have a lot of expertise about that. And perhaps in light of discussion before, a little bit of standardization at least is useful for this community as well. I think there are links to that could really be explored there. WMO since a couple of last years really pushes for open data for exchanges. So I'm sure they will be very interested in hearing more about the potentials for changing, and from the numerical value prediction point of view, which is my background, absolutely this data is very valuable, and we moved away from the let's say pure meteorological data, which is done by the meteorological standards to now basically all data, including crowdsourcing and the other. So this data can be provided, for example, from the wind farms, it's much higher quality, I would say, than the crowdsourced data, which is already being used. Very much welcome.
Yeah, I mean, that's why we did this effort in with the recommended practice on the quality requirements of methodological data that is well collected and delivered at or around wind farms and solar parks, and we have of course also been looking into the WMO standards to kind of come as close to that as possible. But I think this really opens a whole new world for both communities to really improve models and so yeah, thanks. That's really good news.
Is that slides? Probably not. No, the last night is that's the extreme events version 1. That's only extreme events. You want to have them?
No, those are yesterday's slides.
Yeah, good.
Okay.
Sorry.
Right. Hello. Most of you know now, but I'm David Lenaghan from National Grid. I work in part of National Grid, which is the electricity system operator, which is basically the equivalent to Air Grid in Ireland. And I'll just spend a little bit of time talking about our journey from deterministic to probabilistic that's taken place through my experience in forecasting wind power in our team, the energy forecasting team. And it's been an interesting journey, not a very direct one, as I'll explain. Yes, unfortunately, my slides seem to have gone astray, but hopefully I'll be able to articulate our journey quite clearly too. So the journey starts in the year 2008, when wind power in Great Britain was maybe we had about a gigawatt worth, and that was considered quite a lot at that stage. And I was in a small team looking at how to forecast that. The market arrangements in Great Britain require generators to submit a forecast of what they intend to do over the next 48 hours. And coal and nuclear generators have become well practiced at doing exactly that and doing it very accurately. Wind farms were kind of new at that, and because of all the vagaries of the weather, which you know better than I do, it's pretty difficult to achieve the same kind of forecastability with a wind farm. So, and at the same time, there's been a very big promotion of renewable energy in Great Britain. So there was an incentive not to burden the wind farms with the need to achieve the kind of accuracy that a coal or nuclear power station would achieve when forecasts. So for all those reasons and more, we had a small team where we decided we would do wind power forecasting on behalf of the wind farms that we had connected at that time. And we started very crudely with gathering as much free weather data as we could. We fed that into a crude power curve. We started by the biggest approximation, just pretending that all the wind farms that were in existence were behaving just like one wind farm, and we just feed it through the equation and get an answer. And perhaps unsurprisingly, our forecast errors were huge at that early stage, and this back in 2008. At the same time, we have many years of experience in electricity demand forecasting, and with all the historical data and everything else that we had, 1% error was kind of achievable as an accuracy level of forecasting for the map. So there was me and 3 other colleagues in the wind power forecasting team achieving 50% error and thinking that was good. And then not too far away, other colleagues in the demand forecasting team saying, well, we achieved 1% error, what are you doing? And obviously, we started to realize how difficult it would be to try and achieve 1% forecasting error in wind power. And we talked to a lot of meteorologists, a lot of weather companies, and we said, well, can we get to 1%? And they all basically shook their heads and looked at us as if we were asking for the Earth and the Moon and the entire universe in a box. No, maybe that would have been easier than achieving 1%, I don't know. But so we had to really scratch our heads. What do we do next? Obviously, drawing a single line out into the future for a particular wind farm and saying the power output will follow that line just isn't going to happen. So we talked to the weather companies again and thought, well, we need to really approach this in some way. And they helped us greatly at that stage and said, the thing you need to do involves ensemble forecasting. And that was a brand new term to me in the year 2008 and 2009. And they basically explained what many of you already know, is that many forecasts are generated with slightly different initial conditions, and that gives you a plume of many forecasts that give an idea of the uncertainty. And that was the way forward. So we started to spec up our forecasting system in 2010, where we wanted to actually do this properly. But there was a big problem. We very quickly realized that the deterministic approach required a certain amount of data. The probabilistic approach required 10 times that data, or maybe 100 times that data, or even more if you wanted to go that far. And we, with some wisdom, had decided we wanted to store all the data, all the forecasts that we receive, all the weather forecasts, wind speed. We wanted to store those for further use in the future. And all the forecasts that our forecasting system, as such as it was then, for all those forecasts that it produced, we wanted to keep those as well for further analysis and all those good purposes. And we realized if we went down the full road of ensemble forecasting, we would be storing gigabytes and gigabytes of data. I don't know if any of you have to wrestle with databases, but we were using an Access database at the early stages, and it did have a habit of, well, there was a danger that if you got to 2 gigabytes of storage in your Access database, then it would just freeze and lose all your data. And you'd have to go back to the copy of the Access database that you had hopefully made before the one you were using exploded. So there was all of that going on, and we were coupling this together. And basically by 2010, we decided we needed a proper forecasting system, spend some proper money on it. It needed to be an Oracle database, and we needed actually to buy proper weather forecasts as well, rather than scraping free stuff off the internet. And we needed to have that continual conversation with weather forecast providers as to whether we're doing the best thing. But still, when we spec'd it up, we realized we couldn't deal with 10 times or 100 times the data. So we had to compromise. We made a decision at that stage to, instead of receiving every single ensemble member, we asked weather companies to convert that into percentile forecasts. And that basically reduced down the data management problem to a level that was manageable by our IT. We were quite worried at the time that when we switched our system on and started using it in anger, we'd feed the forecasts in one end and have to wait 2 hours to get the forecast out the other end. Really, 2 hours too long. Wanted a much quicker turnaround. We set ourselves 1 hour as the absolute longest processing time required to get from weather forecast to wind power forecast. So by making that decision, we were able to do that, and also one surprise in the middle of the IT project, that not only do we want to forecast the by 2010 we had about 15 wind farms that were directly connected to our transmission system that we wanted to forecast. Then we realized actually there was a lot more behind the meter in what we call embedded wind farms, and we also it started to dawn on us that we really needed to forecast those as well. And unfortunately, our colleagues in the IT department, we hadn't been quite upfront with that. It was something that kind of came to us partway through the IT project to say, actually, it's not just going to be 15 wind farms, it's going to be another 100 of these really small ones we need to forecast as well. So after a bit of tension, we managed, and because of our design decisions as well, we were able to forecast all the wind farms we needed to at that stage and meet our target of delivering it in 1 hour. So that was great. it was a success. In 2011, our Oracle database forecasting system came to life, and we started forecasting. Errors were about, we managed to push it down over the following few months down to about an average of 5% error for the entire wind fleet that we were forecasting. With the maximum error per month, we were tracking as being about 20%. And yesterday I talked a bit about ramping errors. It was those occasions that really made our errors increase. So that's kind of where we got to. But now we're on a journey again with increased commitments to scaling up the amount of wind power that's connected to Great Britain's transmission system. At the moment, we're at about 25 gigs, and there's plans to double that in the next few years. Really, 5% error is, well, 5% error on 10 gigawatts is one thing, but 5% error on 40 gigawatts is a different story. 5% is not going to be good enough for us. And as I've said, these ramping events are a real pain. So basically, the point that I'm coming to slowly is that the design decision that we made in 2010 to turn ensemble members into percentiles, we're going to have to revisit that very soon, because doing that filters out a lot of good information from the ensemble members about ramping events, about the timing of possible ramping events that we're finding now is really important. So we're going to have to go back, revisit our design, and start with the ensemble members individually, feed them all through the forecasting process and get ensemble members in the power domain. And then only at the end of the process, turn them into percentiles to gauge on the service. So that's kind of the gist of the journey. But I think I should say a few things about my colleagues in the control room. They're all very good people and very diligent engineers. And they've always been a bit in two minds about probabilistic forecasts. On the one hand, it's very important to point out that our control systems and our software in the control room is actually really expensive to modify and to adjust. Really need a big justification to improve it, to extend it, and there's lots of other reasons and other requirements that we need to meet. So that, for that reason, that's quite a barrier to flowing the full benefit of probabilistic forecasting all the way through our process into our control room. That's one barrier. The other barrier really is that, and it's not really a barrier, I think it's unfair to say at that, but even with a deterministic forecast, an intelligent control engineer knows that life isn't going to turn out exactly like that. They've looked at enough wind power forecasts, probably more than I have, to know that if the forecast says that a ramp is going to happen at a certain point, then chances are it may happen 4 hours earlier, or may happen 4 hours later, or anything in between. And they already know that. They don't really need a probabilistic forecast to tell them that. So they might say, we're getting on okay with what we've got. One of the mantras is, if it ain't broke, don't fix it. So that can be right for today, but for tomorrow and the future and 3 years from now, might not be quite the right answer. So that's really where I hope to set the scene for my future presenters, just to latch on to some things I've said. So thank you very much for listening. Next one, George is next.
While you're preparing, David, I have a question. Maybe there are others that have a question, but I think maybe one of these questions I do agree that operators have really a good feeling. They are actually thinking probabilistic, but there are two things in this. Number one, as things change, like if there is a huge increase in renewable energy, what they know from the past years may not hold in the next years. That's one argument that you can come to your operators. The other thing, so change is always, when things change, our experience has a problem, or we have a problem with applying our experience. So the advantage of using a probabilistic methodology is that that can deal with also change. And it helps, it can still help the operators to make that informed decision by having an objective method to on the uncertainty, to compare with your own feelings about, or experience, let's call it experience, not feeling. And something like that can also be put in a deterministic system. And maybe this is a way of getting to the next level.
Yeah. So keep discussing with my control engineer colleagues what is the way forward. When they're getting to the point where the tools that they currently have and they currently use are not sufficient in their own right. And when we get to that point, that's when a big change will happen. That's when a new tool will be reached for, and I think we'll get to that point quite soon, where my colleagues in the control room will say, actually, yeah, we need to rethink this. We need to think probabilistic. We need to get more data, more ensembles. We need to redesign our systems. But actually stood the test of time for a long time, but we're getting to the point where they may not.
How much are you inspired by other TSOs? Like what this story we got from Gregor with their DS3 development program internally?
Yeah, I'm very inspired, and I had a good chat with Connell this morning about different TSOs. I had the pleasure of visiting a few of them over the years to see what they do in terms of wind power and more in general about their system operations. And I think one rule flows through all of them, that necessity is the mother of invention. So the TSO that has the most pressing problem is the one that's going to fix that problem first. And the TSO that doesn't have that problem wouldn't be motivated to do anything about it. So different TSOs, it'll be the one with the most wind power that has built the best system to manage wind power. It'll be the TSO with the most solar that's built the best system to manage solar, and so on. And I do wonder which TSO will have the most electric cars to really figure out what needs to be done to manage the electricity flows with a significant amount of electric cars.
Norway.
Norway. Okay, good. I'll go book my trip there. But that is so true that the TSOs, and I'm sure it's true in business generally, that when the problem is here, it tends to get fixed. If the problem's over there, then it's easy to delay, and there's always other priorities that get in the way, and this problem doesn't get fixed or addressed until it's right on top of the TSO or other company. So I think that is just the way of the world. I've, as much as I can internally, tried to be proactive on certain issues. It's quite difficult until the problem is, until it's agreed that the problem is a big enough problem to have the right amount of resource applied to it. And that's, yeah, it's just the story of business. Okay, right, I should hand over. So, thank you very much.
Thank you, David. So, hello to everybody. I'm going to present a similar journey actually to the probabilistic, but a bit from the academic point of view. Although during the years we took on board lots of industrials, and I think it would have not been possible to have this journey without the industry. So, okay, I have this updated figure for the state of the art. And in wind forecasting, it's good to remember that the history of wind power forecasting started around in 85, where we had the first publications on time series models, purely time series based on data without weather predictions. Then we started to have more works in 1990, actually, where we had a new generation of researchers like myself. And we started to develop statistical models, physical models. It was a time that at RISO they developed Predictor, University of Oldenburg, the Previento, and other models. And numerical weather predictions started to be considered as input to the models to predict wind power. And then each organization had a kind of hybrid system to do predictions, actually, that they were collaborating with industrials to apply that. So then by 2001, we decided to join forces in some large collaborative project, which was called ANEMOS, with 23 partners. Actually, at that time, the European Commission wanted very, very big projects. And we tried to do some systematic work, first to do a mapping of what existed in the past. We organized the first benchmarking, which is still valuable actually in terms of conclusions, etc., with 11 models that existed already, all of them deterministic. We started to develop models based on artificial intelligence, combination models. It was the moment where we had some nice works from the Carlos III University of Madrid, where they illustrated that the combination can bring value compared to the individual models. And then this became actually mainstream approach, with Red Eléctrica de España being the same, the first TSO to have operational a combination model from, but it was deterministic. Then we had the first probabilistic approaches. And the concept at that time was that, okay, for 10, 15 years, we had deterministic models, and we did not want to lose all this experience that was gained until then. So the first probabilistic approach was a kind of plug-in or behind the deterministic model in the model chain, just to provide uncertainty estimation, the PDF, based on the deterministic base forecast, but considering it was not just an estimation based on the error, but was considering also it was conditioned on the weather forecast, etc. This was the main objective of the work also of Pierre Pinson, who did that PhD at that time. Then we had upscaling approaches for regional forecasting, etc. And with that standardized things, and we had some evaluation protocol how to assess the accuracy, which is still valid actually. And then there were two, this was between 2002 and 2006, and then there were two similar projects, Animus Plus and SafeWind, which aim to develop research in collaboration with weather organizations to numerical weather predictions dedicated for renewable applications, direct probabilistic predictions, not to have this two-step approach, but have directly the PDF generated by input, RAM forecasting, predictions for extreme, for cutoff, etc. So it was the first time we saw also some probabilistic RAM forecasting, and also generation of other types of products like scenarios ensemble risk indices. And we had actually in the SafeWind project a portfolio of new solutions that appeared. Classical direct probabilistic forecasting scenarios, so ensembles, which had to be calibrated. Spatiotemporal methods, it was one of the first objectives of SafeWind, to use data from neighbor sites. This probabilistic RAM forecasting, tools to warn or alarm for large errors. I mean, when we try to realize at that time that sometimes we cannot improve the forecast itself, but we can anticipate what will be the level of error and warn the operators to adapt their decisions. A new concept, which was the risk indices based on ensembles. We tried also for intra-hourly predictions variability. We knew that we could not predict minute by minute, but there was some work, I think it was from me, so actually to predict the variability during a specific hour. This was very interesting. And then to try to find, to estimate some predictability maps that could be used also together with resource assessment to assess investment when income was generated by participation in the market. And this was already back in 2012, 10 years ago. And at that time, our community was facing some skepticism by the power system community, because they were saying, okay, now everything is done in wind power forecasting, there is nothing to do anymore. And when we finished, and this was the reason why it took actually 10 years to the European Commission to finance, to open a new call that would, for improving the renewable predictability. There were lots of projects which were applying forecasts, but not really projects to do research on improving forecasting. And then I remember this is from my presentation at the final workshop of SafeWind, where we thought this potential we could see and the tools. We just dare to say, okay, that the forecasting, if this is the wind power forecasting technology curve, we are not here where the financial says, but we are at the beginning of this curve. Was this true? Well, at the time we defined lots of R&D directions to improve predictability. And it's like what we want to do today in this workshop. What are the gaps and what we have to do next? And here I will not present them, but you can consult and maybe we can check what we said 10 years ago and what remains still valid. And here are the big directions, let's say, that we had identified. Some of them still remain of interest. And then what happens? As wind and also solar installation capacity increased, we saw a kind of explosion of the international interest in terms of publications. Here is a research. It's from the thesis of Rosemary Brown with Jethro. We have some similar also plots where you can see the number of publications per year. And here is where we stopped our 3 projects, Animus, Animus Plus, and SafeWind. All 3 of them produced something like 250 papers in conferences and journals. But then this was at the beginning of the curve, and this somehow justifies that there were, I mean, if you have papers and academic research with results, this means that there are things to do. So this count, how to say, it's an argument against what they were saying, that everything was done. At least if you give money to the academic community, we can produce results. It's clear and papers. So all these R&D and the directions had as objective to improve the accuracy, actually. There are many things that you can imagine for at the level of weather predictions, post-processing, etc., data to improve the accuracy. But at that time, we saw that lots of things depend on the applications. And when you have all these models and different products, there was a clear need that you need a kind of intelligence layer to combine this information and optimize the decisions that you can take from the use of forecasts and increase actually the value of the forecast. And this actually motivated us to introduce a bit the concept of value-oriented forecasting. which is a bit different on the accuracy from the accuracy-oriented forecasting, which is the baseline of the forecasting community. So if I complete this figure, by 2019, we developed a new project actually in which we have partners like Ricardo, Gregor, Kerpanson, etc. And we have some, we said, okay, there is a lot of incremental research and we need some disruptive ideas. And so we work, I say here some keywords, but I will present later two of these ideas. The first one is seamless forecasting, ultra high resolution. We saw from REMCO presentation with LUS, advanced numerical weather predictions and seamless weather predictions by Met of France, prescriptive analytics, tools for extremes, the work on data sharing that was presented by Ricardo, new forecasting products for applications, and also forecasting tools that are able to be resilient and robust against missing data, etc. And also optimal use of forecasting applications. Now this is a bit a journey of, let's say, the forecasting part. When we go to the applications, forecasts are used in a large number of applications, either in power systems or for trading. And here we can enumerate some of them, like unit commitment, economic dispatch with optimal power flow, fast dynamic security assessment, scheduled maintenance, reserve setting, congestion management, wind storage coordination, storage management, energy trading, ancillary service provision. And also we have, with development of smart grids, we have, let's say, new configurations of energy systems which need forecasts at a smaller scale, like smart homes, energy islands, microgrids, etc. The baseline, how to integrate uncertainty and the probabilistic aspect at the early times, this was before the 90s, and it's a picture for a more care European project where we had two cases. One was Ireland. We were collaborating with ESB at that time. And then the second was CREED. And we developed, for example, a unit commitment tool to integrate to optimize the dispatch of the units, taking into account wind generation. At that moment, it was a challenge to integrate the unit commitment, the wind production, and what the constraints it improves. So at that time, actually, we did not have stochastic optimization, we did not have probabilistic models, and what was done, and what was really done now also in real practice, is just to define a margin of, let's say, 30% of the load, above the load forecast, and this would define some spinning reserve that would permit to compensate for uncertainties. And the tricky thing and the advanced thing is to have a dynamic definition of this margin as a function of the time, actually wind penetration, etc. So this was the advanced thing of in 90s. Then appeared stochastic optimization methods and more lately robust optimization. There are works which are quite, you can find an extensive literature in the last 15 years. They mainly use scenarios, which can be ensembles, or quantiles, for example, that come from PDFs for robust optimization. However, what we have observed, and we often repeat, is that there is a big mismatch between what is developed in academia and what is applied in practice. The adoption of probabilistic approach is limited. A first attempt to see what are the benefits of probabilistic approaches in power system applications was done actually in that Anemos Plus project between 2008 and 11 I mentioned. But still at the time it was too early to adopt the tools that were tested and to deploy them industrially, because the reason was simply because the renewable penetration was not that big to motivate an operational change of the paradigm, actually. So just to see, because this is quite important, in that project we developed 15 tools. It was a demonstration project that we tested with at real sites with TSOs, DSOs, and other end users. So, for example, we had one operating reserve setting tool for TSOs that was tested at REN and also at Sony AirGrid. And this was one of the few tools that later was actually, after the end of the project, was deployed industrially by REN because they saw the value of the probabilistic approach and they wanted to have it operational. This was developed by INESC. Then there were tools tested for congestion management for REN and for EWE in Germany. Wind power trading tools based on stochastic optimization by tested at Donk at Axion. And here I have some highlight results. Also, stochastic unit commitment was tested here for the case of AirGrid Sony as a common system. Because these were partners of the Animos Plus project. And the idea at the time was to take a stochastic model that was developed by Rizzo, the Wilmar, and adapt it to the stochastic paradigm. This was very difficult. And why this was difficult? Because if you want, the operational tool that was used, it had taken so much time to AirGrid, etc., to fine-tune, to have all the right parameters of the generators, ramping costs, starting times, and all this, that was impossible, practically impossible, at least in the frame of a European demonstration project, to transfer this accumulated knowledge in a new tool so as it could give the same quality of result. I mean, the basic difficulty was to transfer from the tool they were using all the representation, the detailed representation of the physical system to the new tool, which was based on probabilistic approach. We had difficulties to do that. Initially, we started with a stochastic optimization tool, and then at the end, what we did was to have scenarios and then run the deterministic tool with each scenario and then probabilize the results at the end. So it was an intermediate way to use the tool, the experience that existed, the deterministic tool, a unit commitment tool, to schedule the system for different scenarios, actually. And then there were also similar tools for islands like Crete with PPC and wind pumping storage optimization with REN. So these are some interesting experience actually. And then we go to 10 years later to Smart4S approach. Probably you have seen the objectives of this project. Here on the left side, I have the overall value model chain of renewable energy forecasting. It starts from with data, then you have the weather forecasting model, then you have the post-processing, the renewable power forecasting model. Then you have services that permit to transfer the data to the end users. And then you have decision aid models, optimization models for the power system management or trading for the electricity markets for the functionalities I showed before. So the objective of this new project that started in 2009 until 2023 is to have an holistic view and optimize actually the whole model chain of renewable energy forecast. So in this model chain, we have actually predictive analytics, prediction tools. We have forecasting models for weather variables, wind and solar aggregations. We can have dynamic line rating. We have also demand or market prices. So this can be actually models that we can have, that we can need for the applications, in addition to the classical renewable forecasting. And depending on the application, we may need different forecasting products, which can be scenarios, ensembles, which can be forecast for extremes, or it can be probability distributions. And usually the forecast we use, they are tuned to, as I said before, to optimize accuracy, and not necessarily, they do not consider necessarily the end result, which is the value they bring to the application. So on the other hand, we have the decision support tools, which are tailored to the different actors. So you can have aggregators, producers, energy communities, TSOs, DSOs with different problematics, and for a multiplicity of problems that I showed before a list. And also we need to take into account the uncertainties because we are in a context with high penetration. So just to show you two directions that we developed that go consider this value-oriented forecasting and also some other aspects that go beyond, let's say, the incremental concepts. So I take here one example of the generic of a model chain, which is the case of a virtual power plant, which is trading in multiple markets, day ahead, intraday, and ancillary services. And so we start with data, then we forecast the aggregated production of the virtual power plant. Here in the parentheses, I have the models we need, so we have one model for this. Then we have to forecast the market quantities, the market prices, the imbalance, etc. Then we have to forecast the quantities for the ancillary service markets, prices, volumes, activated probabilities, 6 models. And then we use all these forecasts to one model that does the stochastic optimization and take the trading decisions and say, okay, what will be my position at what time at each market. So in total here in this chain, we have 11 models actually. Here we speak only about this, only about the renewable forecasting. And we have to know that, okay, we can make huge effort to improve this, but if we lose accuracy here, then we lose the value at the end because all of them are jointly used to trade. So we have a lot of challenges, independent, which is the big amount of data, data reliability. We have a physical system that changes because a virtual power plant, you have connection or disconnection of renewable plants, multiple uncertainties, and also you have a high dependability of data because of the models, for example, here, the forecasting models with data. So here you need, especially if you have forecasts, if you have storage, you need, for example, to have a specific forecasting model for each time frame. For example, you need forecasting models for the very short term, if you have storage to manage the storage, for the next hours, for the intraday market, and also for the day ahead. And what happens usually in renewable forecasting is that we develop a separate model as a function of the data we have. This is very evident in photovoltaic forecasting, where we develop models that use into account, for the next minutes with sky cameras, for the next 2 hours with satellite images, etc. So one of the objectives we are working on is to simplify actually this complex model chain with multiple models already only for the forecasting part and achieve a kind of convergence of the technology. So this means, what does it mean? This means to develop a kind of seamless approach where we have one model that's able to consider all the available data, to cover all the time frames, and all the renewable technologies together, or their aggregations. So it's a kind of holy grail, it's a kind of high-level objective we fixed. We have quite interesting results. So rather than maintaining multiple models for different time horizons, to have just one. Then another direction is to think completely different from this forecast and then optimize scheme and replace all the steps by a single model. This can be done using artificial intelligence, decision trees, artificial neural networks, etc. And it considers jointly forecasting and optimization, actually. In reality, what happens is that we learn from the data the policy, how this process goes to the decision. So we learn the mechanism to go to the decisions. So from the data, we go directly to the decisions, actually. Then we have first proof of concept, and we have comparable results with some publications and at attribute transactions, etc., with a full model chain. And what happens is, here is really horrible, we skip the probabilistic forecast and we skip the forecasting optimization actually as intermediate steps. And this is really, it's an approach which kills forecasting. So that's why it's completely maybe heretic for this workshop. But what happens is that, look, here the data we have are deterministic. The measurements are spot measurements. Even if we have ensembles, it's a specific input. And what we do is, when we go through these models, we increase this information through the probabilistic models, quantiles probabilistic information, and still increase. And then finally, the output of this stochastic is still one trading decision each time. So we start from something which is little information, we increase it, and then we end up with one value or some values every 30 minutes for the next day. So yeah, like this, it's a kind of simplification actually, because it's not the same thing to maintain one model and the same thing to maintain 11 models. And when we do this, we can have some methods that give also good interpretability. So it's not a classical artificial intelligence where you have black boxes like neural networks. This can be done with prescriptive precision trees. And also we evaluate this method to go to higher resilience. I mean, here you can we develop methods now in the project where when you have a problem here at this level, missing data, erroneous data, or from cyber attack or anything, then still to get a decision here. And this is very important to have a model which is robust on the problematic information. And then with this approach at the end, we can also integrate information on the human in the loop more easily than in the previous process with the classic models. Okay, so just to conclude, some, let's say, big directions that I personally see is in the future, what we are going to see is clearly need for new forecast products that probably we do not imagine yet. As for example, in 2012, or at the beginning of the previous projects, we could not imagine the risk indices or the warning systems, etc., etc. And this will be requested by emerging applications we can have. And we have a nice deliverable in Smart Forest for that. Then what will be for sure a good direction is to work on the simplification of the model and value chain. This will remain a challenge because it helps the decision making. Also, we spoke today, the automatization of the model chain is something that's needed. Then we see that for the classical model chain, we see that we can have today different products, different forecasting tools, but still we don't have optimization tools that are able to consider in an automatic way, for example, around forecasting, probabilistic forecasting, and risk indices. So it will be interesting to develop this kind of tools that are able to combine it. The integration of the human in the loop. I mean, it's interesting to imagine that in the future, when it goes to application, you develop solutions that consider the operator, they are operator-centric. This has some implications. Finally, the big keyword now is resilience in power systems. So we see it with the crisis now. And here we can speak what I mentioned before about the models that are robust to missing data, cyber attacks, corrupted data, etc. These are methods that permit to enhance with resilience the tools that exist, and it's very important for the future. Even the question of extreme events, etc., integrate somehow all this question about how to come up to a resilient system. I mean, that is able to deal with these difficult situations. And finally, we speak a lot about probabilistic and why they are not integrated in business practice, because the appropriate tools actually exist in the academic literature. Right? There is a huge literature, but often we don't consider this. Actually. And there was in a previous workshop a nice presentation. I have to find it. I mean, if a company today would like to really change the paradigm and change the tools from deterministic to probabilistic, they need to apply a kind of, let's say, scientific process of innovation adoption policy. They need to have to put in place some methodology to permit to their personnel to adopt in a proper way the new innovation, actually. And this may appear a bit abstract, but when you speak with, let's say, human resources or managers that have also the responsibility in companies to introduce innovations, you can see that there you can have a very scientific and very interesting approach and aspects that you never imagined if you are from just from the modeler side, where you develop a model and then you say, okay, my model is here, why you don't use it? Actually, it's much more complex to adopt a model in the real practice, and you have to follow a kind of human-centric innovation adoption approach. So here is where I would like to close. I was a bit long. If you want to follow Smart4S, here are there is a page at LinkedIn. You can register to the newsletter of the project. There are some nice webinars where you can have detailed information about this aspect, some of the aspects I presented, and that's all. Thank you. Questions? Yes, but the reference for this validation is a full model game, and we have all the models for renewable forecasting, etc., special optimization, and here you have the revenue that is generated in the market based on real data, etc. So the objective is to have at least the same revenue as the full model game.
Bringing in AI into decision trees, and I think that would be useful in some instances. So if it's standard behavior, they're going to be very good at predicting. So there's huge advantage to not having to do all the computation. But like, if you give that anything out of the ordinary, we're seeing more and more extreme events happening now in the weather. They do not do well at all. So how do you know when can we use these new tools to reduce the computation versus when? And do we need the standard ones that are more robust?
If you have, for example, extreme events on the weather forecast, these are predicted here, and you use a random forest, and we know that random forest, the problem is that it can learn what it has seen. It cannot learn. So even here, you will be missing this. So, well, this depends a lot on the method. I mean, because a learning process, how if the AI model you have is able to how is able to deal with rare situations and unseen situations. This somehow is also the objective of the robust approach with missing data, because it's the same thing. I mean, having missing data one moment and to have to switch to a model that can operate without this data is also a way to hedge against this kind of problematic information. Because extreme events are problematic information, I need some outliers, etc. So the question is how you can have something which is robust to problematic information, actually. So, but probably either you have resolved it here, and then you consider this special optimization, or it can be resolved in the input, maybe with ensembles that can consider these extremes at some of the members, or it can you can resolve it in a robust way, maybe that.
I've got one question just to throw in. You've clearly explained all the tools and techniques and systems. So I was wondering if you were tempted to, instead of following the path you have of waiting for a system operator to implement your good research, why not instead try to do forecasting as a commercial service and wait for system operators to come and buy your forecasts directly? Was that considered as an option?
Well, for our case, we are a research center, so it's not our mission to provide commercial service. Now there are many companies that provide this kind of services. What's important is to be able also, because we speak about technology transfer and adoption of tools by end users, but what's important in this process is to make some technology transfer to the companies that can commercialize this. So this is a different question. But of course, it's one of the objectives also of the European Commission when they put money to this research, because here we are at TRL low, between 1 and 4. It's not a demonstration project, but then maybe the next step is to demonstrate these approaches in realistic environments and then to commercialize them.
Thanks very much.
The next one, yes, the one is Juan.
Hi, yeah. Yes. I have sent you my presentation this morning. I don't know if you.
Yes, I got you. No, I got you.
Oh, perfect.
I got you sent. I'm just trying to find. Here, get going. I'm trying to find Justin's because he had also.
Perfect. So, hi everyone. My name is Juan Sopena, or you can just call me Juan. And today I wanted to talk to you about what users want at the end of the day. And I would like to share my insight that I have developed during my PhD and after. That I had the opportunity to keep working on energy forecasting, but in the industry. So one way to get this, users at the end of the day, they want forecast with some values and they want another value to know how good is that forecast. So if you can go to the next slide, please. Thank you. So just for those who don't know me, I was a PhD researcher here in Ireland with Vikram Pakrashi and Elisha Goss from Trinity College. And we were developing a project focused on reducing the cost of operation and maintenance of onshore wind farms in Ireland. For that, we were developing forecasting, wind power forecasting algorithms, also other algorithms such as downtime detection. And after that, I'm still working on the development of energy forecasting tools with my company, Solute. For example, we are releasing soon a forecasting tool for operators of wind farms called Fowler Wind. That if you're interested, I can tell you after this talk. But this is not what I wanted to talk about today. If you can move on, thank you. So one question that, the first question that I had when I started my PhD is how are wind power forecasts modeled? So I was doing a lot of reading for my literature review, and I tried to summarize. I'm sure this figure here is not complete, but I was trying to summarize how are they modeled. There are many different preprocessing or cross-processing techniques to preprocess the data, to post-process the results. Many different forecasting models based on time series analysis, vector autoregression, autoregressive models in general, all types of artificial intelligence models. But not only that, is the fact that these forecasts are estimated in different flavors. More traditionally, as we have talked already, as point or deterministic predictions, and then probabilistic estimates, such as probabilistic density functions, quantiles, prediction intervals. And of course, to understand all these researcher efforts can be understood when we are trying to increase the share of renewable energy in the electricity mix of countries. For example, if you remember Connor from INESC mentioned yesterday that in 2030 in Ireland, the aim is to have an 80% of electricity coming from renewable energies. So this forecast will only become more valuable in the near future. But the problem is something that we have mentioned before as well, is despite having so many modeling methodologies proposed in the scientific literature, of course, everybody claimed that whatever they have done, their forecast solution is the best one and the one that provides the best forecasts. This problem comes from the fact, well, there are many things that are explaining the situation. This is just a brief list, but the first one is the lack of standards to evaluate wind power forecasting models. I think this maybe comes really in line with the guidelines that, for example, that have been developed already with the Wind Task 36. But if everybody is using their own standards to evaluate their models, it's impossible to compare them. Then, due to the importance of wind power forecasting and energy forecasting in general, everybody wants to jump in the wagon, develop their own models, even if they don't understand the data or anything related to energy or weather forecasting. And they think, well, I have an artificial intelligence models. Let's throw some data and see what happens. So this leads to the second point that appropriate experimental designs are not there in many cases. Then another point that I am really happy that it came up in the previous open space session is that we are not always selecting the best or the most adequate performance evaluation metrics. As you know already, in the case of deterministic predictions, for example, we would go for scores such as mean absolute error, root mean square error. But ideally, to better interpret this forecast, we should, for example, normalize by the capacity of the wind farm, or use relative scores so we can interpret and compare this forecast among the results of different wind farms with different models. Then, of course, the data sets that models are using are not representative because they do not have enough data, or this data have not been quality controlled. And one more important that is not is not only related to wind power forecasting, but to the scientific world in general is. In some cases, they are not, at least not enough details to reproduce the experiments. They are not providing what parameters their models have. So we cannot even reproduce at least whatever they have done for our own comparison purposes. So benchmarks. But of course, in the academia is clear. Of course, if we have a new whatever new forecasting model, that we want to know if it's actually good, or at least it performs similar to the state of the art. These benchmarks help us to get fair representation of our model. And I have realized in industry this is also important. For example, for a specific industrial case, we might have a pool of models that we have developed, but might not always work for a particular scenario. I don't know, because maybe there are some specific weather conditions in the area we have our wind farm. So we want to get the best model to provide the users the best forecast solution for that specific case. When we are developing a benchmarking framework, of course, first of all, we need our forecast to be fair and representative when we are evaluating them. So the evaluation sets we are using, they have to contain significant operational conditions of our farm. And before starting the benchmark, there are some key points that we have to take into consideration. One that I believe is very important is the prediction horizon. Because depending on the prediction horizon, the sources of the predictability might vary. For example, if we want to develop a benchmark for a solution that is aimed for very short term, then we might want to pay attention to historical, to recent observations of the wind farm or nearby weather stations, because that will be the main source of predictability in principle. Then following up from there, we have to adapt to the data we are using to that. In this case, as I have mentioned, for example, for very short term, use recent observations and historical data of the wind farm to train our model. But if we are moving further ahead, then we have to pay more attention, of course, to NWP data. As I have mentioned already, we have to ensure that this data is representative, both the training and the evaluation splits. For example, we could check the distribution of both to see if they are similar or not. And then use standardized performance evaluation metrics all along the way. I think this is also very, very important if we are trying to move to probabilistic representations of wind power forecast. As something that I found very interesting when we were talking before in the open scenario is that, of course, when we are developing a probabilistic solution, we get a predictive density function. Then, of course, we have to check the reliability of that distribution function. We have to check the sharpness of the distribution. But these are things that maybe an end user in the industry they don't want to hear about these things. They just want to get a value that is providing information from there. So we could use some other metrics that are a bit more simpler to understand. For example, this is a workflow that I designed during my thesis, where the probabilistic representations were provided in the form of prediction intervals. So to evaluate them, we were using two different metrics to evaluate the coverage of the interval in the evaluation set, and another one to evaluate the width of that same interval. But we could use some others, for example, such as the Winkler score, that penalize incorrect prediction intervals, and try to convert this in something that can be understood easily by end users in the industry. Well, for example, in the context of winter, we were starting to develop a benchmark for very short term, where we were using data, scalar data from two iris wind farms. We had this data recorded at a turbine level with high resolution. We had in total, I think it was 3 years of data. And so also what we did to maximize the representativeness of the result was to create first some splits of the data containing around 2 years of data each. So we could evaluate the model under different evaluation conditions, such as the ones shown here for one of the wind farms. Of course, in this case, we have in the first 2 data sets, we have some periods that for one reason or another, they were either no recordings or the connection of the turbine with the SCADA system was not working properly. So we discarded these 2 data sets in the final evaluation because they could bias the performance of the models. So in this case, just to start the benchmark, we were using some models where we were using a pre-processing step using decomposition and different artificial intelligence models. But of course, I have mentioned this would be only an initial benchmark where we should extend it to other state-of-the-art methodologies, as I have mentioned before. For example, in the context of very short term, we should check this result with persistence or vector autoregression. And we should extend the result to probabilistic representations of those forecasts. These, for example, are this matrix is the one that is evaluating the width of the interval. It's just a percentage value. But of course, all work is work in progress. So the first point that I have used this as a baseline to keep implementing state-of-the-art models for in particular case study. Then in the case, for example, in this case, I have mentioned that I was using decomposition algorithms, but there are some parameters that are defined by, in this case, by the user. So we should take into account the effects of selecting one or other values for those parameters. And third, we'll extend these results to other data sets, ideally open source or another regions of interest, to see if the results are biased by any particular conditions of those wind farms. And and this was just an example we were developing with our forecasting tool in Solute, that we were trying not to replicate this benchmark in particular, but we had some models and we wanted to check which ones were performing better for a specific case for one client. And we had more models developed for this specific case, but at the end, using a benchmark where all these steps are standardized, we just get the results of the ones providing the best results for every case. And this is all. Thanks for your attention and any questions.
Just go back to your can you tell us what's the usual operations are just eliminating the zero values effectively here?
Well, so in this case, in the context of this project, the data were pre-processed already. So, well, a third party gave us already the data. So I only had to do some small filtering, considering well some non-values, so trying to correct them. But most of the data were already pre-processed, considering all these things. So it's a step I didn't have to do in this case.
You didn't get access to the raw data.
Yeah.
I want to say, what is slide 8?
This one?
No, yeah.
Here?
This one. Yeah, this one. Here you have different methods. Like.
Well, so in this case, well, I mean, this was just, I was, as I said, I was trying to see the performance of some algorithms combining a pre-processing step, decomposing the original data, and then different artificial intelligence models, such as, well, based on, in this case, on neural networks, for example, GRU or LSTMs are recurrent neural network type of models. And then I was combining them to see the effect of using one decomposition algorithm of another, and then what neural network models were performing better in this.
Which one do you recommend?
So one point that is very important is that I'm not saying that any of these models is better than any other model existing in the scientific literature. What I'm saying, so the important point is not only, of course, the models that you are using, but to have standardized way of working that you can find the best, the best forecasting model for a particular solution. So in this case, and I'm just talking in this case, without use other state-of-the-art models that are not considered here. There was particularly the composition algorithm, although they have other problems, that is called BMD, variational multi-composition, that seemed to work better than others. And then in this case, I was feeding the model with data from the own wind farm. Well, every time sequential data, it seemed that recurrent neural network models were the ones performing better. I don't know if that answers your question.
I think I would like to make a comment and a promotion, because I think we have tried in the recommended practice part 2 to make such a pre-standard recommendation that we have been working on here over a number of years. That's about benchmarks and trials. And maybe you can take that home, and everybody can take that home, that if we try to apply this and use this, what we have developed now, and use the task here to evaluate, is this good enough to have that standard, or do we have to make adjustments that will, I think, will help us all to get around these kind of problems that I mean, many of you maybe also are asked to make such an evaluation, which is the best model. And if we all start to use the recommendations that we have been developing, then we can also file proof them and see, have we actually done our homework, and have we really made the right recommendations, and evaluate this at the end of the task here and say, do we have to make adjustments? So maybe everybody can take that home and recommend this next time. And I think also for anybody who is doing reviews, this is maybe something to take with us, that it is correct that often there are publications and articles about experiments where there is details missing, so you could, even if you had all the data available to make an experiment in your area with that method, you can't really know whether you can't do it because there are details missing. And I think this is something that is important, that these kind of details are provided.
Yeah. Just add that nice thing too to have just a public web capacity that trial. Just say like, hey, it's independent, too. There's, IE8, Sentinel Link, then there's also, you have the long version, and then there's also like a one pager, there's summary pages that are really, a lot of clients want to read through the whole thing, right? Yeah. Something easy to read that has, recently take home some of those points.
Yeah.
I think another factor in why everybody's method is the best is that you tend to optimize your method for the data set, the location, the time of year, whatever you're working with. You run as many models as you can to get the best result for that location.
Yeah.
And then maybe you try another location that you tinker with the model a little more. Right? So naturally, you get a really good result because you're customized for what you were trying to do in that specific problem. And I think that's part of it. I mean, all the other issues you pointed out are certainly valid, but that's another issue that when you compare things in literature, everything's optimized for that one problem.
Exactly.
Actually, I have one section like you have got some methods there. So, and sometimes this may happen that we don't know which one is the best. So there is something called multi-fidelity approach. So in those multi-fidelity approach, you have multiple methods, and it would be like you can think about that averaging out. Okay, so that would be the nearest analogy. So so if you use multi-fidelity approach, then it would just give you better response. So and you will have all the methods here with you.
Okay. I didn't know about that.
You will search about multi-fidelity.
Yes, another aspect to the benchmarking. I know it's not easy, but when possible, the testing of the different models in real time, it's important. When you, in some way, you estimate how it will work in real time. It's not always, it is not always true, and this assumption is not always play the same role in the model. So,
when I get
real-time validation is something that change the
truth
results of the different benchmarkings when you
yes. Exactly. I mean, no. The point that you are raising is completely valid. Of course, once we are trying to use a model operationally, then this kind of issues come up. Especially, I mean, the only solution for that is to monitor the results and see if there is a decrease of performance, at least to a certain threshold that you consider is good enough to retrain your model if you have new data available, or check if there is a shift in your data distribution that is indicating you that maybe your model is not going to keep performing well. So, but of course, one thing is benchmarking, another is the reality.
But the idea is to benchmark the reality.
Yes, I mean, of course.
Yeah, just to add up on that, like forecast demonstration projects are something that really works in operations and metrology, which are rarely organized. But another flavor to the performance, which is often overseen in publications, is significance results. So basically, people test models, different models, and you have no idea whether the difference is significant or not.
Yeah.
It's crucial to tell anything about whether one model is better than the other.
Totally. I agree with you.
So rarely we can find this information in applications, and I think that should be really a part of the benchmarks as well.
Yeah, totally, I agree with you. I don't know if there is any other question or. Thank you.
Is that?
He doesn't have he hasn't prepared anything.
Okay, good. Lovely. One down, one to go.
Yeah, so while Gregor is trying to find my my presentation, we are a bit more than an hour later than we are supposed to be. And I'm kind of wondering, maybe I'll ask who in the audience has been playing the game, or maybe the other way around, who has not been playing the game? 1, 2, 3, 4, 5, 6, 7, 8. So the question is, I mean, I had planned to let you all play the game, but if those 8 can commit to play it today or in the next a few days, we can maybe save half an hour and get a little bit back into our schedule. And I really would like to encourage you to play it, because it's where it's interesting for us. It's giving us a lot of interesting and important insight into how do we deal with decisions, and how far are people in understanding, and do we have to change something when we present it. So maybe I can get you to play, and I'll then present kind of give a little bit an insight of where we are right now. We have been last week making some first little analysis after we had reached a bit more than 100 participants, and where we get some kind of result that we can say this is significant enough, because a workshop with 20, 30 people doesn't give us a result that is representative. So maybe very quickly, the initiative has started in task 36, and there is a new work stream, the decision making under uncertainty, that we continue on, and there has not happened so much yet for those that have kind of signed up and wanted to be part of it, because we are still running the experiment that we have started in 2021, because we just didn't have enough participants. And it's part of the IAA task 51 now under the work package 3 and decision making work stream 8. And it's carried out in collaboration with the Max Planck Institute for Human Development. We have a cognitive scientist, as she's calling herself, Nadine Fleischhut. And this is kind of a collaborative work from the Lexicon project that is funded by the Hans Oertel Center. DVD is also involved in that sense, and we're trying to make this work with having funding from different sources, and I think it has been quite successful until now, and I'm very happy that the German Weather Service is also really supporting this. So jumping into the game, we had made kind of 3 postulates in the start, where we said success in trading is highly dependent on the cost of balancing power needed to due to forecasting errors. And it's maybe not only trading, because it's also the balancing. A system operator would have the same kind of problems, but just not so much on the financial side, more on the physical side, but it's a little bit similar. We have about an experience of about 5% of the cases with large errors are responsible for 95% of the costs or the errors for balancing. And in a month or a year or a decade, whatever we look at, and reducing these costs is kind of more important than improving the forecast by 1 or 2%. That's what we have heard yesterday. Also, Malte Riek from Vattenfall has provided this nice example from their analysis, where the best forecast was then not creating the lowest costs, or then vice versa, the highest income. So that was kind of the outset, and then we had developed let's call it a scheme with high-speed shutdown. This is where probabilistic forecasts are important, and where we want to know the risk about cutoff wind, and we have then designed a kind of, we have designed an experiment where each we have cases, and it's a bit simplified, that it's not like in the power market, you have to have each quarter of an hour or hour. We have taken a range over 1 day where you have to decide whether there will be a cutoff event or there won't be. And if there is a cutoff, you should trade less. And if you think there is no, you should trade the full amount. And in the first experiment, we had an offshore wind farm where it's really usually about 23 to 28 meter per second. Now we have taken in the second experiment here a wind farm in complex terrain, and there we can see that there's shutdown of wind turbines already around 20 meter per second in average, and this is because we have strong variable wind and gusts that easily go up to 30 meter per second, while the mean wind speed still is much lower. So that's the kind of the outset, and we then provide pre-deterministic power forecast, as it is often done in or used in industry, and often a wind speed isn't provided, but we said we provide one, so that there is a bit more equal outset of the information. And then we provide a power forecast and wind speed forecast from a probabilistic model, from an ensemble model with 75 ensemble members, with a multi-scheme ensemble prediction approach that is kind of valid in each. The uncertainty that is created with the multi-scheme ensemble approach is there is a valid uncertainty in each time step, so it's quite useful and a correct method to use for this kind of problem. And then we provide a cost table. So if the trading with 100% takes place, or is the decision, and there is a high-speed shutdown, you lose 5,000 units, monetary units, and if there is none, you gain. And then if you trade less, because you think there is a high-speed shutdown, and there is a high-speed shutdown, you don't lose anything. But if there is none, you also only gain 2,500. And we have not provided this kind of cost function, but some of you may have thought about, and if I provide it, I don't know whether the results will be different, because we have here, of course, such a cutting point with respect to the high-speed shutdown probability that could be used when playing the game as a strategy to decide when should I choose the 100% or the safe solution with 50%. So the game is set up, as most of you know. We have each participant has to make 22 decisions with the deterministic, and then the blocks are randomized, so you cannot. It has been tested, and I believe that the cognitive scientists have kind of an idea of how to and what to randomize. that you really can't remember the cases when you go to the deterministic, and it's also randomized. So not everybody starts with the deterministic and then goes to the probabilistic. There are also some when you start with the probabilistic forecast first and then go to the deterministic forecast. And there is a reason for that that I will explain in a moment. We then also wanted to know about the confidence, and maybe some of you have been wondering why we start the confidence at 50% and go to 100 and not from 0 to 100. And I have also been wondering, but Nadine, who is working with this a lot, said that, well, it's a common understanding in psychology that confidence below 50 is kind of, I'm just guessing. So, so it should reflect that under 50%, I would only be guessing. But the further I go up, the more I'm sure that I know what I'm doing. So this is how, I don't know whether everybody has understood it in that way. I got some feedback along, and we may have to explain this in the next game a little bit better, but and this is also something that we saw when we looked at the first results, that there is maybe not everybody that has understood it in that way. So that's then the same, as I said, for the probabilistic. And normally we should play now, and maybe some of you want to use the break to grab a coffee and play. The link has been sent by Gregor, so it's still in the invitation. And please, I will check and I will send around an email if there are 8 more by the end of the week that have been playing. Okay, so I'm just, of course, making fun. So let's have a little glimpse into the data we have collected so far. The very interesting thing, in a way, because we are always interested in who is the winner. And the winner right now is a person, Amelie 6, that has got 42,500, let's call it euro, with a deterministic score. And everybody that is working with probabilistic forecasts gets tears in their eyes. I'm also one of them. But of course, we know that we are in a group of, or whatever data we analyze, there are outliers, and outliers are not representative. So that's how I try to keep my humor up when I see such a result. The interesting thing is we have the highest score with probabilistic is 32,500, and so we have actually two with the deterministic that are above that. But the interesting thing is then, I don't know where we can see this. This is here at the final balance looked upon with a box plot, and we have here the mean and the median, and we can see here that outlier. And but what we saw and what is interesting is that there are a little bit more. I mean, I wouldn't call that so much significant yet, and that's why we want to collect more and have more participants than 100. In the last experiment, we kind of ended with 115, and this time we said we want to see whether there is a more significant result coming along the way. But the interesting thing is that we really have more, you can see this, we have more on above what we call all things and God's eye. And we have made this, we have made these levels because this is where also the 50% chance is, where if you just randomly not think about or look at the forecast and just randomly take a decision, you should be around here. And if you take all safe, you're always on the safe side. You should be around here. And what could be a bit worrying is that we have not so many that are kind of getting close to God's eye, so making the right decisions all the time. And you probably can't make all decisions right, because we have also built in 1-2 cases where it's you would be very sure that you take the right decision, but you will do the wrong decision because the forecast is wrong. And that is something that every operator experiences. And we wanted to see also and look into the effect. And one of the next experiments will go a little bit deeper into that effect in looking at does that change our confidence and our performance if we have made a mistake, even though we were kind of sure that we are doing it right. So we then also looked on, are those that are good in the deterministic, good in the probabilistic, and vice versa, are those that are good in the probabilistic, because we have slightly more that are around here than we have on the deterministic side. And we can say, yes, some people benefit from the probabilistic, some don't. And we have this across all levels. So you can see here that you have one that is up here and down here on the probabilistic, and vice versa. This some go kind of okay, but we see very rare the horizontal lines. So we can't really see that one benefits or doesn't benefit. And that's kind of something we have to get our head around a little bit more, and also think, does that have to do with the design of the experiment? Or so we can see that overall 35% of the decisions differed between probabilistic and deterministic, and that's kind of, we don't have something to compare it with. So this is just kind of what it is. So we haven't really been thinking so much about, is this good or should it be higher? My feeling is that it should be higher, but maybe it shouldn't. So then we looked upon the proportion of correct decisions. So correct categorizing of, if there is a high-speed shutdown, did people also make the right decision? And we can say unfortunately, so this is the high-speed shutdown, this is no high-speed shutdown. And we can see that in the no high-speed shutdown, we have it's slightly worse with the probabilistic than with the deterministic, funny enough. But on the high-speed shutdowns, here we can see this stays a little bit better, but on the if there is a high-speed shutdown, seems like the probabilistic forecasts are better, or people are making the correct decision rather with the probabilistic. And so why is this? Is there a better identification of the high-speed shutdown? I would also say that maybe in some cases, if there is no event, the probabilistic forecasts can confuse, because there is always some kind of probability that event could happen. And then it depends on what is your strategy on how to interpret the probabilistic forecast. So, and then it also, of course, reflects the asymmetric payoffs. So because you lose money when you make a wrong decision, and you gain something, but or you don't lose if you are safe. There is a kind of a bias in the kind of decisions. And now I have to think about, because yeah, it's this with the more safe choices. we have about 60% that do the safe, and we can see here it's also it's showing up kind of that with the probabilistic forecast, people are more safe, and that's kind of interesting, because in a way this is good and in a way this is bad. Because we want people to be aware of risks, but we don't want people to not take a risk when it's kind of safe to take a risk. So the proportion of safe decisions is kind of higher, and then looking on the mean confidence, you can see all the participants here, and it's kind of a little bit difficult, and we can see that across all participants there is a high variance, and the mean this is not a significant result. We cannot consider this significant, so it's almost the same. So and then we can of course expect that the mean confidence should be around 75, but we have to start looking into kind of patterns, or what are here. We have to actually look upon the outer edges where people are very non-confident and very confident. And one of the questions we ask in this respect is, it's often said that with a deterministic forecast, you can be overconfident because you don't know the risk. You filter this out, and that's why the result is kind of is meaningful, that with probabilistic forecast you become a little bit more risk averse. That one was a little bit shocking when we saw it for first time. So because we would expect that the confidence, whether the cognitive scientists say that if the confidence is calibrated, it should be along that line. And that means that if I have a high confidence, I should also make the right decision, and vice versa. If I have no confidence, there's chance that I make a wrong decision is higher. But what we see here, is really there is no calibration so far. So is this because it's a difficult task? Are participants trying to avoid losses rather than being correct? So because we have this asymmetric cost function that you can lose or gain less, that can of course change all the confidence or the thinking about when to take a risk. So that's kind of reflected in the 60% safe choices, and then it's kind of equally in cases with and without. So we cannot see a kind of a pattern that it's better with the probabilistic forecast. And of course, that's why we also ask ourselves, has the definition of the confidence and influence on that some people may not have fully worked or understood it the way we intended it to be, but so that's why we also said we need much more participants, and maybe also talking about the game, it will change, and that's why I also encourage people to play it again, because that gives us the possibility to see that if somebody has been playing it and then maybe has been at a workshop or heard or saw some of the presentations that we have been providing, that this changes the strategy, and we can then see a different pattern, and we because that's what we want to analyze and see. So that's why we have made it in this experiment in such a way that you can change your name, your ID, But then we have made a unique ID that that shows us if you run again that you have been there beforehand, and we can filter this because in the global analysis we have to filter second and third and multiples out, and then we can look on the multiples in a different perspective. And that's why I also say go home and play it with your teams or your in groups. This is all part of our interest. But of course, if we make the global analysis, that's where we cannot do it. So then learning, that was also kind of interesting. I think last one, is there an effect on the order? Is there, are people making better decisions when they have started with the probabilistic and go to the deterministic or vice versa? Or is there any kind of effect? Normally there shouldn't, but we can actually see an effect. And because it's randomized, it's really, we can kind of say there is a security in built in, that we can see that those that have started to play with the deterministic are making better decisions with the probabilistic, and those that start with the probabilistic make less good decisions in the beginning. And that can, of course, have multiple reasons. One thing is that you have got used to the concept, so you're more confident on that level, or it is easier to think from the probability, from the deterministic once you have kind of get your head around, and then you get the uncertainties. It's easier to make the decisions. We don't know, but it's an effect that we have seen. So that was kind of a first glimpse into the data that we have collected and analyzed. And yes, as I said, it's still open to play, and we will run it at least out in 2022. And as data comes in, we make an analysis. Yeah.
Thanks. Prediction performance doesn't really correlate with the flat lines.
Yeah, the first one.
So if you use color in those lines,
yeah, that's a good idea. We can see this better.
One or the other, then there might be more colors going upwards.
Yeah, that's a good idea. Thanks. Mm-hmm.
The perspective of a user of the competition. So at some point I felt, I think I started with probabilistic forecast, if I'm not wrong, and I felt in the middle some lack of trust, I think, on the forecast, because at some point you start to make errors, and you don't understand if it's because of your internal mental model that you use to make a decision, or if it is the forecast that it's not correct. In terms of calibration, for example. So some kind of a feedback might be useful, because we have a long sequence of tests, and at some point you start to play randomly, because you lose all the trust you have in the forecast on your mental model. So that was my personal impression.
Mm-hmm.
Something about the confidence, because the thing with confidence, this has been something we study in Smart for Has, is you need to relate confidence with the size of the intervals, of the percentiles of the forecast. For example, if you want to be confident, if the intervals are larger, you are more confident than that, and you don't miss so much. So it might happen that this calibration that we didn't have in confidence is also because we don't adjust the forecast to the expected level of confidence they want. This has been something we have been discussing in climate change.
Yes, I would say yes, I agree to a certain extent, but we don't adjust the confidence levels if we use a multi-scheme ensemble, because that is generating a physical uncertainty that we don't adjust in a way that we say this is a statistical confidence of a percentile 95 is in that hour, and it has nothing to do with the past. So that's why in that application or that test, we can't do that because the uncertainty is generated from a physical ensemble. So that would be a different case if we had a statistical approach where we then could say we adjust the confidence levels. But it is an idea that with another application and where we use such a method, that something like that should be maybe built in. I think I know that the cases are not simple, and it's also that the randomized order is of course changing. If you are unlucky, you get this one case where you will most likely be wrong at some stage where you maybe have just made a mistake beforehand and you make another mistake, and that's where we lose confidence. So I think it's really good to get that feedback. I'm really happy, but I can also see that my methodology works because it's not about that methodology or that these data. It's also how we react and how that affects our confidence level, and whether the probabilistic forecasts then help us or do not. And we can see right now that it doesn't look like it's helping us on the confidence. Yeah, Gregor.
Maybe I've overlooked that, but showing the confidence for every play, you had that one, but that doesn't show the sequence, so to speak, right?
The sequence.
It's not the results. It's just
this is number the proportion of correct choices and the confidence, but. If you just have the confidence and the sequence, then in this case you would see sort of that kind of a curve, and then you could also have the points with a right decision, wrong decision.
That's what we have to do. And we have to maybe also look upon the difference in sequence, and how that changes on the.
If you drop in confidence after a mistake, it might be.
If you can find not so much a question as just an opportunity for me to basically open but I think beyond this, to kind of using stuff like this as a teaching tool when I obviously work about teaching for games and things like that. I think the one thing that's hard in real life that's slightly missing from this, that would be too complex for this, is here there's no opportunity for a person to really, there's a right answer essentially, right? Yes, there's those two wrong cases that you built in there deliberately, but in theory, you could automate this whole thing and a bot would play perfectly because there's nothing for humans to subjectively pick up on that's kind of, where the forecast reaches its limits or whatever. And I do wonder in practice when we're teaching people to use these things, you kind of come up against this limit where we teach people, hey, look, it's a probabilistic forecast, here's the rules about how you interpret it, you can draw your kind of expected value curve right at the start. But how do we teach people to more methodically and structurally combine their intuition with probability, because that's a very fuzzy process itself. And I know you've been working with science to do this, but I do wonder with games like these or whatever, how do we teach people to actually be able to do this in real life, where the kind of rules that you're following here or you learned with this game, you can't necessarily apply them directly.
Yeah, and thanks very much for that question or comment, because that's why I brought that one, because this is something that you could kind of use as a rule. Like if the probability is over 33%, it's better to trade 50% than 100, and that's one of the things that we kind of try to understand also here. Do people have a consistent strategy that they follow? And then, as Ricardo said, if I have decided on a strategy, like for example, I'll look at least 30% probability or a percentile 30, and if there is more than that, I think it's probably I'll take the safe option, or vice versa, or I take whatever over 50%. And that's why we at the end ask also about what strategy have you been using, and sometimes it's difficult, but also have you been looking at the wind speed? Like some people said at the end, and we have really very funny comments at the end on the strategy. I totally forgot the wind speeds. And I can see now, if I would have looked on the wind speeds, I could have seen that some of the cases that where I was wrong were actually, I could have seen it on the wind speed. And but that is then again why we say it's of course simplified. But I have heard so often also in the control room that you need to have something and you need to have a strategy. And building that strategy is quite complicated also for a group of people that should decide in a kind of a uniform way, even though the uncertainties are varying very much. And does such a strategy hold? But that's what we also want to try and see, is there an effect on certain things when the forecasts are wrong? Because that happens all the time. I mean, that happens no matter how good your probabilistic forecasts are, they can be wrong. And but yeah, I think there are probably 20, 30 extra small games that we could play to get more of the details. And but I think this is only a start. I mean, the psychologists say, yeah, but we can also get we try to get funding so we can pay people to play, because then you can just take 1,000 people and let it play and then see the effect. And that's kind of where we are working towards, to have more funding, because I think it's an incredible smart tool to understand where are the barriers, how do we have to design things, how do people learn, and how do we have to teach people to make better decisions by having more information without having just a bot that we decide whether we believe in what is coming up or not.
So one thing that's not provided is any information on the quality of forecasts, so how well calibrated the probability forecasts are, or the errors of the deterministic forecasts. So if you're a user and you're trying to assess your confidence, you don't know how confident you should be in the forecast. So it'd be interesting if maybe a second experiment, you provided that information, right? So now the user has some idea whether he should be more confident or not. And maybe that's part of the reason why the confidence of the users has no relationship to the actual outcomes, right? Because you don't know whether you should believe in the forecast or not.
Maybe I would actually like to give this question to David. Or is there anybody else that is with, no, Corinna is gone. In the control room, do you think it would be helpful for your forecasters to know how good calibrated your forecasts are? I mean, I'm just picking up, I think it's valid, John, what you're saying, but we also, I want to kind of get a feeling, is this something that is that we need also on a practical level, and that is used?
I think it depends on the amount of time the person making the decision has. If they have 2 seconds, they might go straight for the safe option, not even look at the forecast. knowing there was no negative downside, and maybe have that as a policy and just go straight through all the decisions, trading 50%. Fine, don't even need to think. Perfect for myself.
But do they react different? Are you making? You probably make analysis of how good your forecasts are. So are you providing this information to your forecasters and say, we have our forecasts have improved with whatever you can trust in it? Does that give them more trust? Or because that's what John is really asking. He's asking to provide the user with an analysis of how good is the forecast.
I think we can't get away from the fact that if we produce a bad forecast, then that inevitably leads to the loss of trust in future forecasts, and it takes a while to build that back up amongst our control room colleagues. That is a definite effect. It can be quite a challenge, and also the fact that we've got 5 shift teams. So if one shift team A, for example, is on shift when there's a storm rolling over and we get big forecast errors and all kinds of problems, then that shift team doesn't come back on shift for a while, but they may still have the mistrust in their mind
when they come back,
even when a perfect forecast comes through from us, and they might say, oh yeah, I'm going to hold more reserve anyway, just in case, run the system with lots of fat on it, just because they've lost faith in the forecast.
So maybe it is worth an experiment to provide that information and see whether it has an effect on people if they know. But it's again it's the extreme events that take our, it's kind of the extreme events that take our confidence.
Just, I think it depends also on the stakes, because if they miss and they will fire them, they will make one decision. If they miss and they will just say, okay, next time would matter, they will make probably another different decision. So what is the level of stakes you have when you make the decision? That's also something that influences the way you make the interpretation of the probabilistic model. So you might be more conservative.
Yeah, that's right. But what David said is something that I have been interested also for a long time, because insurances have the same thing. They have seen that their brokers are not providing the same or are not making the same decisions if they get cases where they have to evaluate whether the insurance is paying the full amount, a part of it, or nothing. And that's the same traders that have had an experience will need to have a trust built up again, even though the forecast would be perfect when they come back. This kind of effect of having a group of people that have the same task, how can we get them to make this a uniform decision? Can we find strategies and tools for them, for groups, to also hold on to the confidence even though they have made mistakes? And that's why I wanted to build a first thing into this to see an effect, and then maybe take it further, because it's a problem that is known in all large organizations where you have a team of people doing such kind of decisions. So
I think if one enhancement maybe for the next version would be to have a timer that counts down 30 seconds, that you either choose 100%, 50%, or you run out of time where there's an even bigger loss attached to that situation, where you're forced to make a decision or have it made for you. That's really the reality in the control room. They're trading off not only the options that they have, but the option that they're going to be forced to take, which won't disappear on the day.
I've seen it just one thing. We have actually made a little experiment on that in the American Meteorological Society conference here in January, where we didn't have so much time. So I made a little Kahoot with 10 cases. And there we had the participants had 10 seconds to decide. And actually there was also kind of music. And in the background, I don't know it because it was online, not everybody had heard that. But the interesting thing was the person that was the winner, very experienced forecaster. He was the previous operating agent together with Gregor in the first part of the task 36. He had one wrong decision, and that was the first one. And because he was kind of checking out all the things that he normally checks, and then it was pen and the gong was there, and he hadn't made the decision. So it was of course wrong, because if you make no decision, it's also wrong. But all others, he had made the correct decision. And we then asked, what did you do? And he said, well, I just took my experience and intuition, and I said, I have to just look at two things and not more. And then I make the decision. And that's, of course, something that we learned, and it's definitely on the list, that how do our strategies and cues change if we are under time pressure. So that's, yeah.
I have one more questions to David, or people who really eye contact with from these companies who use it. Seeing all the problems that we have of understanding how people react and are subjectively influenced by things. I mean, at least in theory, the ideal is to have you can calibrate a system, and then you have the mathematically the perfect system. The best you can do. Do you think the error will be how much will people be taken out of the decision? Say we try to make it totally automatic, or as much. How much can you make decisions automatic? Or is it just that you say legally it will never be possible to say that just an automatic system will make decisions?
I think that's a similar question to when will we see planes flying automatically, fully automated with no pilots. It's the same kind of thing. There's a certain comfort factor in having to step in. The user might go astray, but yeah, I think people wouldn't be comfortable in an airplane just purely computer flight. Would you be comfortable?
I guess this is what we have seen also with the cars. I mean, some human has to make this decision how to decide in an unknown event, and we have seen with the cars that if the algorithm has to decide to drive over a child or rescue the people inside the car, who is taking that decision? We are humans and we make mistakes, but having an algorithm, still somebody has to decide, and that's the same in an airplane or whatever. And I think it's also in a system operation, there can come up situations that we haven't seen before, where a human being will make a better decision than an algorithm.
From what I hear, I have the feeling that the player is actually the game, and you are the player. I don't think it's not. It's not the players who play your game. It's you. Your game. The subject of your game is actually the players.
Well, yes, that's why we call it the probabilistic games and experiments initiatives, because it's really experiments. that we design to see how people react. But to make people, to give an incentive, we make it as a game, so it's more fun, I think. But yes, you are right.
The way you speak about humans, etc. And then my question, because I was wondering, what's the difference between a game and training? Because at the end of the day, the operators would like some training, like we have a flight simulator, but what's the distance between developing this kind of games and developing training systems actually for taking decisions, integrating some feedback when you because when you train, it's related to what Ricardo said. You have to understand what was your mistake, because you learn by trial and error. And if you don't see what is there or what's the reason behind there, you cannot learn.
Yeah,
so what is how far we are with flight simulators for probabilistic tools?
I think it's on the list, and we definitely have a kind of started focusing on this to see once we have finalized this. I really want to go into a phase where we decide where do we go next. And the training is definitely, I have got a lot of feedback from also groups that said this was really useful to discuss things, to get discussions going inside the group, and but to make a training tool, I think that will be a slightly different design, and but it's certainly something that that we should discuss here in the forum and in the community. What should be the next? Should it be a game again? We just thought when we started that making a game is something people are more relaxed because it's just a game. Whereas if I should go to a training, does that kind of give people a little bit more skepticism and this? Because we saw these three barriers: skepticism and mistrust and misunderstanding. And that's why we wanted to first go the game way, to make it really, it's not realistic, it's not really the situation that you or anybody is making to get started. But we definitely, I want to discuss this. Where should we go next? Should we make such a training tool? And how should that look like?
I think an immediate thought is that each time you make a decision and you make an error, you get some feedback and you see in this process if you improve your next choice. I mean, the feedback can be whatever it is.
Yeah, but of course, you want to see the learning.
You see immediately the answer and say, okay, now you made a mistake because the forecast was wrong. So see if you can adapt based on this feedback.
Yeah. So that's why it also requires a different level of funding. That's clear, because such a training tool is much more complicated than such a game in the setup and analysis and so on.
Yeah, just on the training, and just a frustration I have with this is that you have two different balancing markers in the same event. In HSSD, you have that you have balancing marker minus 50 and minus 100. So does that factor into your decision making? It's certainly factored into my decision making later on in the game. And could this be run with when you trade 50% for HSSD? Could you run that at minus 2.5?
Yeah, we could do that, and I think our results also show that there is a bias due to this asymmetric asymmetry in the conditions. The question is just what is more realistic, and when we designed the first game, that was kind of the feedback we got in the beginning, that it costs more if you make a mistake. If there is a high-speed shutdown, then if you play safe. And that's why it's this balancing, and that's again the training. I think the training effect of making correct decisions independent of any financial incentives or financials, or and we have to look into the results when we have more participants and see the effect, and then but in a new design we have to take this definitely more into consideration. What is the goal of it? Do we want to see correct decisions, or do we also want to see such an effect of an asymmetry that in the power market, at least in the trading, that exists?
I think you would need to maintain common balance and market price between the two events in order to, because if you can't have the 2100% is penalized twice, whereas 50% is only penalized, say, for 50 euro megawatt hour. So it's just to have apples with apples, if you understand. Just that it's for me anyway, it makes it cleaner if you have maintained the same price.
Okay, yeah. So I'll take that home. Thanks. And I think
we're seriously over our coffee break. So let's go and then have a relatively short wrap up in the end.
Problems that we all come with, but they almost end user problems. So the trader that makes a loss, or the grid that's not balanced, we all have these different problems, but they sort of stem from the same limitations in the forecast, and we all have different solutions to them. A solution that we have to produce might have to be done tomorrow or next week, whereas actually being able to talk to you guys where the solution could be put in place much earlier, or the improvement in the forecasting, the base meteorology input variables, or how the models are developed, almost even the discussion about metrics and how we all have the same problem with them, how we communicate what is best for each other. And having that different perspective, I think that's what's really valuable to me.
George? Just try to keep you on your toes.
Okay, so for me, also it's very valuable this workshop, because you can see that the problems we are trying to solve are very complex, and you need to put together competencies from many areas, actually, methodologies, etc. And in the past, it has been more difficult because the different communities were working in a silo, and there were not much interaction, and it was difficult to put people together to work, and to produce added value. This is something that's progressively happening, and I think the task contributes to that. There are several challenges for the future, and it's a state-of-the-art workshop, and the result should be able to try to identify what are the gaps and the challenges for the future to go ahead, so that the work we produce to be useful. Somehow find the right priorities where we can put together our knowledge, etc., and contribute with new knowledge. And this is a big challenge, because we see that, well, we are on the research side, we see what is developing and the development. There are lots of works. Personally, I receive, one paper to review every day or every 2 days. It would have been impossible. It's a full-time job to review the academic production. So one challenge is to see where is the innovation, where is the added value from the innovation. And I think, okay, in all this amount of work, and I think this is very much linked also to the applications, because when we develop something from the forecasting side, weather predictions or power forecasting, it should reflect some value at the end of the day. I mean, you don't do forecast for doing forecast. You do forecast because you want a secure power system operation, higher penetration of renewables, reduce the CO2s, integration with other resources. So we have these are the objectives. And doing forecasting is a means to reach this objective. So we have to, at some point, to be able to integrate in the way we reflect as forecast the impacts of this forecast. And this can be a filter to identify what are the innovations who have the highest potential to have an impact, actually. So, and to recommend them to the industry. Yeah. Of course, if someone finds the forecasting system that has rather than 20% error or 1% error, not in terms of installed capacity, but percentage, like you do for the load, and okay, then you skip all the rest. But we are far away from that.
Corinna?
Yeah, I have also learned a lot, and one of the things that that I find amazing here in this forum and group is that there are always coming new people along, and everybody is really contributing. Also, some of the people that may not have been saying so much. I think I have learned a lot in our discussions, in the open space discussions. Also, when I talk with people about the work we have been doing, and that is really valuable. It's valuable to make a strategy of where we can help, bringing, as George also said, bringing the different parts together, that the end users, the vendors, and the research, because without doing this, we all live in our own world, and we are a small community that is not very much recognized because we are not generating money. We are saving money at our best with the forecast. And that's something that has little value in our finance-driven world and society. And having that community here, and I'm extremely happy that I have been seeing people and touching people after 2 years of COVID. So there is a lot to digest from our discussions, but that's the best, and that's also because they can continue in the breaks. That has a lot of value in comparison to the online stuff. And I love the working group online meetings because we can meet independent where we are. But for the common meetings where we really bring our ideas, our problems, our challenges, and discuss them through all the aspects, that is extremely valuable.
I have to say, leaving the coffee breaks at the duration that they were, even though we were maybe slightly delayed in the program, was a deliberate decision, because I think that's also one of the valuable things here, that you can talk to a lot of different people during those breaks. So how far are we from the 1%, and what have you learned else?
My impression from the meteorological side was that meteorological models are pretty good at this point, but there's still areas of research that we need to tackle, and those are, for example, we talked about the extremes, subseasonal forecasting or seasonal forecasting. There was talk about high resolution modeling, LES simulations. We talked about ensembles and uncertainty, and but what was sticking for me that was maybe, since we are pretty far, maybe the next step would be to just, like everyone else I think said, like come together so that the meteorologists know what the forecasts are being used for, and then we can tailor them better to what people need. That starts with just the definitions of what we think everyone understands, but maybe you know, or that likewise the users come to us and say, this is our problem, so what can you offer?
I think that's also tying somewhat into the narrative that we had
over the last few years or so, that it's the application that determines what actually you should do from the forecasts. And if your application is price forecasting, and you want to have a probabilistic price forecast, then you need to analyze all the ensemble members individually and not just get the PDFs of solar, wind, temperatures separately, because you need these correlations. So it's application driven. If you just want to have the wind power forecast, then we do that already pretty well. For me personally, it was interesting to see that speed of execution actually is already an interesting problem, that once the meteorological forecast comes out, it takes only a few minutes until the market actually reacts in part quite drastically. And that what I also hadn't really on my screen was that huge list of energy meteorology inputs, meteorological inputs to the power system. Most of them were sort of, if I think properly, then I might have gotten some of them, but that the list actually is getting that long was quite an interesting eye-opener. Do you have any comments? Did we miss out on some of the learnings of this workshop?
Well, to me, the major takeaway that I have is really how it confirms the premise of Task 51, forecasting for the energy-driven, a weather-driven energy system, because we looked at all the discussion on correlated events, right? Where you looked at the human behavior, you looked at hydro, you looked at demand, as well as wind and solar. And so the problem is very interconnected and very broad. And I think even the group we have here still is somewhat heavily weighted towards wind and solar, right? And so I think the challenge is the broadness with interactions beyond the wind and solar, which, there's a lot of inertia, a lot of 6 years focuses on wind and somewhat on solar, right? And the theme of the task is broader interaction. And I think we're moving in that direction. The discussion here really confirms we need to move in that direction. But I don't think it's that easy, right? There's a lot of inertia, so we focus on wind and solar. And I think we need to broaden the discussion and broaden the interaction. And maybe future workshops, we need to try to bring in people from the other communities. And they're all listed in the work stream, right? Where they interact with all these different groups. And the discussion here really confirms we should be.
What I've heard at least was load forecasting and price forecasting as some quite important steps that also fall somehow into that remit and that need to be done.
Yeah, I think so.
I'd just be interested in hearing from people who have not been involved in this task before, IA task 36 or this one. What did you get out of this? And how do you see the role differently now than you saw before we started this work?
For me, it was interesting to see, for example, since I have been a PhD student, spending getting into the research paper in the recent few years, and it was interesting to see the actual methods that are being used in the training companies. For example, yesterday's technology presented by IBM. Today, methods of actually the results in the case studies. And also the author some of the papers that I used to follow in my work that I had a chance to meet them in person. Very interesting.
I think in terms of training, I think the practices, the recommended practices you produce, I think from my perspective, not necessarily from academia, I think that they're very accessible, very readable, very ingestible. And I think that really helps, when you're trying to understand a particular topic that's as diverse as meteorology right through to trading. There's a lot of intermediate steps there, but I think your publications do very well in providing that information and, making it understandable to a more common audience, and I think you should continue certainly with that. And particularly, Karin, you mentioned about the glossary, and if we're all speaking the same language, we have multiple languages in this room, and I'm talking about just terminology. So if we had a common language, I think that would certainly improve and speed up the, our discussions, because we can then, I know what you're talking about when you talk about a confidence interval, or, you have said it before, about prediction interval versus confidence interval of 1 year publications. That was a very good explanation. So I have a good I have a sort of an understanding of that now. But in terms of embedded generation, at what point do we do the cutoff? Is it 1 meg? Is it 5 meg? Where are we talking about? So just I think that that glossary, that explanation, I think that really will go a long way to making it more accessible to more people and people understanding what we're trying to communicate.
Yeah, I also think it's really important that we're not so much discussing about which method is the best, or who of us care with the best method to forecast wind power, but to really think about how to compare methods and such stuff. I think a single person can find a new or cannot come up with a new method for wind power forecasting, but a single person can't come up with a standard. Many people have to agree on standard or best practice and on which metrics to use and such stuff. And I think it's really good and important that we have communities for that.
You mentioned the 2 papers per day for review. And I thought that
1 paper every 2 days.
Whatever. I mean, in terms of manageability, that's a small difference. But I was thinking, once we have this workshop and the paper wrapped up, one of the things we might want to do is actually having a guideline for reviews of those papers. What are the minimum criteria that they should have, and maybe have a good benchmark data set that all of those should actually conform to. Which brings me to a short question on, we've seen was it in your presentation of the solar forecast arbiter? Is there work going on for the wind forecast arbiter?
Not at the moment because of funding.
But it was.
I think there is a little. Talking to the guy who's working on it at Kathryn, he said that's in the plans. I'm not sure if he's got funding, but I know the last time I talked to him, he said, "Oh yeah."
Last I heard is that some people were talking to DOE to fund that because it's much cheaper to fund the extension of an existing thing to wind than it would be to reinvent the whole thing again. And they did a really good job in that solar forecast arbiter, has to be said.
Yeah, so maybe I can add one thing, and this is, as I said, the recommended practice is a start to make us look into standardization, or have at least a common understanding how we want to evaluate, how we want to make selections, how we want to help the industry to make the right decisions when they select a solution, and that they also understand that if we have a complex problem, we cannot evaluate with a simple metric, that there is more to it also, and there is more to just the metric and the value. And I think once we kind of start in the groups, in the work streams, we do have a broad range, and we have seen in the kickoff meeting, there were people from biomass and hydro, and the IEA Wind Executive Committee has been encouraging us a lot in all tasks to kind of penetrate into each other's tasks wherever we see something that where we can provide value to each other. So and we have seen this especially in the part 4 of the recommended practice. We had the solar people in, and I had people from the LiDAR task providing valuable information about remote sensing. And that's really what we have to work on. It's we can see how fruitful this is to bring end users, academia, and providers into one room, and broadening this. I think this all the work package participants and leaders, or work stream participants and leaders should remember that we invite invite people to even follow us and follow in these tasks, and find those tasks where we have most interest, and work on them. And I think this is really it's a unique forum, and we should definitely continue on broaden this into the entire energy system.
It's actually a good point, maybe also for the next workshop that's planned for next summer as seasonal forecasting. We could invite, or we could try to make a joint workshop with the solar task and the hydro task. That might make really good sense and would be also quite inspiring, I think.
I was going to ask if is there a task related to electric cars? I know they're not.
Yeah, there's
weather related, but from a user perspective, on my own list of things I need to deal with as a system operator, the rise of electric cars, I can see that being a big problem for us. And there may be a weather-related element to the behaviour of electric cars and how well they charge in cold weather, and how often they're driven in various weather conditions, how much energy needs to go through the electricity system that would have previously gone through a petrol pump, and just scaling up our grid to be able to manage that kind of energy flow in the future. Those are massive challenges for us, and I think weather will have a feature in there, but there'll be other considerations as well. So that I wanted to sort of put that out there as an area of concern for ourselves, that we're interested in any assistance that can be, and any thoughts that can be given.
Yeah, there is an IAA task, right?
I think there is one. I'm not totally sure, but there's over 40 IA tasks, or IA TCPs.
We'll check that out and invite them to our next meeting. I think one of them. It's usually the easiest way to invite them to participate.
Yeah. Can be interesting also. There were some European calls to develop tools for management. Some grid aware, smart charging, etc. And the objective behind which was clearly stated was to optimize the integration of renewables, because you have a kind of, not only the forecasting that can be interesting, that can influence weather forecasting, that can influence the behavior of the drivers, but when you have grid aware management of electric vehicle fleets, you want to couple it with the way you want to manage the renewables, the production, and so on. And probably we can identify which projects have been accepted on that call and see what they develop. Yeah.
Okay. We'll have conversations about that, I'm sure, in future days. But I don't want to labour electric cars too much, because we could spend another 2 days talking about.
On a side note, how many of you actually have an app that shows you the next 24 hours electricity price for yourself? And how many of you have started to use that only this year?
I've been using it for several years, but it's maxed out at the cap. Yeah.
There's no cap in Denmark.
Oh, that's good. related to electric cars, but demand side response in general, this issue of circular forecasting, forecasting, closed loop forecasting, where you make a prediction that might influence the very thing you're trying to predict, I think is also an underexplored area. Especially in this multivariate setting where we're talking about forecasting, demand and price, and then the very existence of that demand forecast affects the price. And yeah, this closed loop effect right now, I think it's minimal, but in the future it will be also be a question.
I put that down for the list.
Yeah, I don't think it was on a list.
Yeah, for sure there are several new applications, and as far as I know, in the UK, for example, in period, there is some works about inertia forecasting for the system like UK, Ireland, which is isolated, because of the future where you have inverter-driven power system, etc., with a small inertia. What do you think about that? Is this a big issue, like for example, EVs? Or?
It's a big issue, but it's probably not very weather driven. For those who don't know, we need to maintain a certain amount of inertia on our grid, which basically means our frequency only moves by at a certain rate. But on days when we have a lot of wind and sun, the inertia level goes down, which means our frequency moves more rapidly if there's disturbances on the grid. That's a bit of a concern for us, especially Connor in this presentation yesterday morning indicated that it's concerned about something called ROCOF, which stands for rate of change of frequency. Without going into a full-blown seminar about it, the gist of it is that if the frequency changes very rapidly, there are particular relays across the grid which disconnect generators. If the frequency changing very quickly, it can be mistaken for the loss of grid influence, which is a real pain, pretty much expensive. But hang on, if you want to know more, come see me later.
Any last words from the panel or the audience?
I was going to say one of the things that I learned, and it might seem like a little bit of a strange comment, is what's not yet possible. I came here with imaginings of maybe somebody's got a fantastic supercomputer system that can simulate 1 centimeter cubes of the entire atmosphere for the entire world at 1 minute resolution from here to next year, and re-update that every hour and supply it all to us. And using that information, we could say, oh yes, at 10 o'clock tomorrow morning, there'll be a cloud right there, and the solar panel will reduce its outputs. Obviously, that's not quite achievable today, but I have learned a lot about what is achievable today and what might be achievable in the very near future. Then what's sensible to ask for.
Yeah, that very likely is also not achievable tomorrow or the day after tomorrow, because we're lacking something on the initial conditions, and then you have people movement that already makes small differences.
I have a comment for that. I think the solar community has tried to do something like this with a very short term forecasting of the clouds. So they started, there are groups that install cameras, and then they started by one camera with take photos of the sky. They try to identify the type of clouds, where are the clouds, where they will move, etc. When they realize that the height of the clouds is important for the speed, etc., they installed 3 cameras. So to have a 3-dimensional representation of the sky
of the clouds for the next minutes. And then you say, okay, you can have, it's a very complex system to treat this information actually, but still you have you manage to detect the clouds, the haze, etc. Still you have uncertainty. The question at this point is to think out of the box. I mean, you really need to go to that direction to think that the mercury is a deterministic system, or do you is preferable to develop the methods that can manage the uncertainties and adapt the decision making and be flexible. And on the other hand, why we develop all this stuff about flexibility? I mean, it's because we want to have this uncertainties, and we have the possibility to have flexibility in the system. So we have to use it intelligently, in an intelligent way. So I don't think that it's worth going to that direction of deterministic modeling of everything. You know, it's.
I agree. Although I said I'm naive in weather forecasting, I do know enough to realise that there's some areas that are science fiction, and as you say, not practical or necessary. So I guess really a thought to leave you with as you're heading home is how much detail do we need to go to achieve good enough? Because good enough is good enough. Perfection might get there, but it's expensive, time consuming, and wasteful actually to build up all your systems all the way to that level. So what's the practical thing to do?
I think we don't get to a better closing word than that. Thanks all for being here. A lot of thanks to UCD and Vikram to host us here and to organize these nice lunches and the coffee breaks, the room, everything. I think we'll have a chance tomorrow to actually thank him in person. For those of you who come tomorrow to the task meeting. And with that, thanks to the panel, thanks to you, and see you in half a year for the task meeting, maybe online, and in 1 year or so or less for the seasonal forecasting workshop. Oh yeah, and thanks to the guys who got up really early in Canada. I'm going to close that now. Bye.